Hello and welcome to the UK SES SSBI Satellite Design Competition Day. Sorry for the slight delay in our start. There's been some technical issues beyond our control, but we think we have everything sorted now. I'm David Sully, the team lead for the Satellite Design Competition, and I'll be hosting today. Just at the start, I'll be giving a brief background on the competition for anyone who is unfamiliar before we start seeing the team's presentations. So on the next slide. The UK SEDS SSBI SDC has been running for 4 years in varying formats. Initially, it was an essay-based competition where teams of university students were tasked with designing a communication satellite and then an astronomy CubeSat. And over the past 2 years, the teams have been tasked with designing and building a 3U lunar CubeSat for a terrestrial environment. The aims of the competition are to challenge students to perform a complex systems engineering task, provide them with experience of industry processes and protocols, and allow them to apply their taught technical skills while developing and enhancing other transferable skills, such as teamwork, planning, and leadership. The competition mission for this year is for students to design a 3U CubeSat that can analyze different sources of data within a simulated lunar environment of a mystery room. So this is a terrestrial room that's got different sources of heat and light, different wavelengths that the team's CubeSat they design has to detect. The competition consists of 2 phases, a research and design phase and a build and test phase. In the build and test phase, the teams would manufacture their 3U CubeSat for the terrestrial environment out of materials and components such as Arduinos and 3D printed frames and hubs for their CubeSat. So the competition deadlines. So there are 2 phases to the competition, where the research and design phase took place between October 2020 and March 2021. The teams in that time produced a preliminary design review and a critical design review. And these were reports which were reviewed and marked by their industry mentors, who then provide feedback to them. The build and test phase was then due to take place from April to August 2021. However, alterations had to be made due to the pandemic. So the COVID-19 alterations. So the continued restrictions on teams entering university facilities have meant that the 2 branches of the build and test phase were completed. So the normal test readiness review on the right side of this diagram carried on as normal, as if the competition would have done without coronavirus. Teams assembled their own mystery room to test the prototype based on UK SEDS instructions and their layout. And the extended design report, which was the other branch, was where teams who couldn't go into university and manufacture their CubeSat could expand their CDR reports to create a realistic systems level 3U CubeSat design for a lunar orbit. The teams could choose which branch they wanted to compete in based on the circumstances of them. So if they couldn't go into university, they could do the EDR, or if they were able to, they could compete in the TRR report. So the competition prize categories. There's several prize categories which we will be announcing at the end of the day in the award ceremony. So there's the overall winner, the best CDR, the best EDR, the best TRR, the best presentation, the best prototype. So teams could either compete in the extended design review or the test readiness review, the EDR or the TRR, as we've previously discussed. So the overall winners will have their scores of their best CDR, their CDR taken, the presentation, and then either the EDR if they entered that or the TRR if they entered that branch. And then the best prototype is a separate award that doesn't go into the overall winner award. So this is the schedule for the day. Not seen on this diagram, there'll also be 5-minute intervals between each team presentation to allow for setup time. We will have 2 guest talks by engineers and project managers from Airbus, who are our sponsor for the competition. And each team will present for 20 minutes with 10 minutes for questions and answers. There is now a Q&A box on the webpage where you're watching the live stream, and we will take questions from the audience after each presentation. There will also be 3 15-minute breaks throughout the day. However, due to the technical issues at the start, we might be eating into the first break slightly, so sorry about that. So the talks by Airbus, at 17:15, we'll have a talk by Robert Hopton, who's a systems engineer on the Envision space mission. And then at 19:35, Ian Walters, who's a project manager on the Solar Orbiter, will give us a project management talk about that mission. So now I'd like to hand over to Tamara from SSPI, who are Space and Satellites Professionals International. They're our co-organizers of this event, and they provide all of our industry mentors who help support all of the teams throughout their whole competition. So thank you, Tamara.
And thank you, David. Um, I am very happy and excited to be here, despite all the technical fun that we've had this morning. Oh, sorry for you guys this afternoon. I'm in New York, so it's still morning for me. Um, SSPI is honored and thrilled to be working with UK SEDS. We are a professional development organization that works with people throughout the entire life cycle of careers in space and satellite. So that starts with students like yourselves, and it goes right straight through to people who have accomplished the very top of their careers and are inducted into our Hall of Fame. We started this partnership with UK SEDS back in 2016, as David showed you, and the goal was to make sure that uh, bright young people like all of you who are competing today are well aware that the dominant commercial enterprise that happens in space is actually in satellite. And so we have been happy to help with UK SEDS develop competitions that draw attention to an industry that we hope you all will eventually find careers in. The topics in this competition have ranged from all the way from small sets to astronomy, and I'm looking forward to your presentations today as long as I can stay. It's actually a Saturday, and I actually had things planned. I just missed that it was a Saturday, so my apologies that I won't stay for the whole thing. But I'm looking forward to your work. I'm excited for the enthusiasm and diligence that UK SEDS brings to this process. And we are grateful that we have been able to partner with UK SEDS to provide mentors um, from industry to work with the teams, to give the teams opportunity to really see what the real world of build and design is like and learn from people who have been doing it and making a living at it. I want to wish all the teams good luck today, um, and let's enjoy the rest of the competition. Thank you. Back over to you, David.
Thank you very much. It's always been great to work with SSPI and all the mentors you provide. You're such a supportive body that really help us make this competition what it is at the moment. So thank you very much. But yeah, okay. So thank you for listening to this introduction, and basically welcome to the competition day. There'll be a short intermission now before we hear from the Bristol team, and then there'll be the Q&A which will be going on afterwards. So feel free to send in any questions that you might have. But at the moment, thank you very much for joining, and we hope you enjoy the rest of the live stream. Okay, welcome back, everyone. So now we'll be seeing the University of Bristol team presenting their presentation. So I'm just going to hand over now to them. So yeah, here we go.
Do I start now?
Yeah.
Yeah, okay. All right. Good afternoon, everyone. So we are Team Serenitas Celestia from University of Bristol. I am Marvin, the team leader. This is Tom and Anna, and we will be presenting our CubeSat designs. Next slide, please. So we have a total of 7 members, and we split the task into different subsystems. I am tasked in attitude and orbit control system. Then we have payload and heating design, communications and data handling, structures design, CAD design, orbit and mission design, and then at last we have the power generation design. Next, please. So the CDR design has several requirements. Next slide, please. So the requirements that we have is to identify and capture images from a lunar surface, from a lunar orbit. Then we have to identify sources of information and objects. We have to detect and identify thermal sources, light sources, and decode electromagnetic signals, and transmit all the data back to a ground station. So these missions will be done and simulated in the mystery room. Next slide, please. So these are the landmarks that we have to capture the signals and the pictures from, and these are the 10 landmarks on the lunar surface. Next, please. The orbits that we've designed in CDR is a highly inclined orbit. The inclination is 76 degrees. It's a frozen orbit, so we don't need to adjust the attitude all the time. Then the altitude that we've designed is around 100 kilometers. It's a circular orbit, and the orbital period is around 2 hours. Next, please. So this is a picture of the orbit ground track. As you can see, it takes around 6 to 7 days to cover all the landmarks. Next, please. So we'll be talking about the CDR design, and this design is mainly for the mystery room and not for the actual space mission. Next, please. These are the pictures of the CDR design. Next, please. So the structure of the CubeSat is a 2-piece aluminum sheet, which is folded and cut by machine. It is designed like this because aluminum sheets are easy to manufacture and design. And the platforms to hold all the payload and the sensors are 3D printed, so they can be in any shapes and sizes. And it's easy to assemble. Next, please. So this is the cost table of the CubeSat. The whole CubeSat costs around 400 pounds. Next, please. And this is the mass table of the CubeSat. And the whole CubeSat weighs around 2 kilograms only. And with a 6 kilogram limit, we have about 68% margin. Next, please.
Our design included a sensor platform controlled using a stepper motor and a reaction wheel, which allowed to rotate cameras and sensors covering a surface of 360 degrees. Next, please. As Marvin mentioned, the platform would be made of a 3D printed aluminum sheet so that a flexible shape design could be achieved. Next, please. The sensor platform arm would be deployed using a burn wire release mechanism. Next, please. And a 5-volt DC small reduction stepper motor was chosen to control the platform because of its low power consumption and high accuracy. Next, please. Payload-wise, 2 Raspberry Pi 4 were selected as main computers, as they are easy to program, have a low power consumption, and high accuracy levels. Next, please. These 2 Raspberry Pi were controlling the electrical system. One of them was dedicated to AOCs, while the other was dedicated to sensors. The Raspberry Pis do not communicate with each other, and they are both connected to the same wireless network. Next, please. Speaking about electrical components, the camera we chose was the Raspberry Pi Noir because of its high resolution and IR function, as it could be used as a backup for the IR sensor. Next, please. Our infrared sensor array is able to capture an object's shape in a high resolution. Next, please. And our triad spectroscopy sensor works as a backup for the camera and has an IR, a UV, and a visible wavelength function. Next, please.
So this is our EM receiver. This fits our requirement for being able to capture the radio signals that are being broadcasted in the lunar environment. Next, please. So this shows a simple flow diagram for how we're going to handle and store data on our satellite. So as Anna mentioned, we have two separate Pis that control separate functionalities in the satellite. We were going to use SSH over Wi-Fi to send commands directly to each Pi, and also we could remotely develop our code and then send them over later. And then all data was to be transferred back on an FTP server that we hosted on the ground station. And then on the left, we have a table of our commands. So to simplify things, we planned on encoding all our commands to a single input. And the table shows each command and then the expected argument. Next, please. So this is our reaction wheel and motor. The top right is a technical drawing of our custom designed aluminium reaction wheel. And this was planned to be driven by a 6-volt brushed motor. So this was chosen so we could keep power consumption down, and we have high accuracy. So that means we have better control over the angular velocity of our reaction wheel. Next, please. Here's our sensor and controller. So as we had one single degree of freedom, this takes reading of our acceleration on our axis, and then we use this to further control our reaction wheel. Next, please. And here's a power breakdown. So these are all values we expect when everything is operating at max consumption, which comes out to about 50 watts of consumption. And assuming that consumption over a 30-minute lifespan, we calculated we need a 25 watt-hour battery to support our entire mission. Next.
So the whole mission in the mystery room lasts for only 30 minutes, and we split the mission into 4 phases. The first one is the startup phase, where after the CubeSat is placed in the room, it starts up all the sensors and the computers. Then is the mission calibration phase, where the sensor platform is released and the sensors are calibrated. Then it is the 20-minute main mission phase, where the sensors captures all the data and send it back to the ground station. Next, please. So this is the diagram of the main mission timeline. The sensors will capture the data for 3 seconds and then transmit the data to the ground station. Then the stepper motor will rotate the sensor platform about 20 degrees, and the sensors will capture the data again, and it loops until the stepper motor rotates the platform 360 degrees. Then the platform resets, and the reaction wheel will rotate the whole CubeSat around 20 degrees. Then this whole process starts again, and until everything in the room is captured. Next, please. So because we cannot access the labs and the testing equipment in the university, we chose to do the EDR design instead of the build and test design, the test competition. And this will be the EDR design of the CubeSat. Next, please. The EDR has additional requirements compared to the CDR because it is actually going to space. So the space requirements added is that the CubeSat has to transmit the data back to the ground station on Earth via a relay satellite. It has to operate in a complete autonomous environment. It has to sustain a 3-month mission timeline and a 2-year maximum lifetime. And at last, it also has to perform end-of-life disposal operation safely. Next, please. So the EDR orbits that we've designed hasn't changed much from the CDR. The only thing we've changed is to increase the inclination from 76 to 86 degree. 86 degree is also frozen orbit, so we also don't need to adjust the attitude. And to increase the inclination, we can cover more of the polar regions of the moon. Next, please. So this is the new ground track of the CubeSat. As you can see, it covers almost everywhere on the moon. Next, please. So the launcher that we've selected is the Eurocot launcher. The cost is around $100,000 US. We chose this because it is the least expensive one out of all the options that we've looked at, and it is very reliable as well. So the deployer that will deploy the CubeSat will be either from Momentus or Astrobotic. These companies do rideshare missions with other CubeSats, and they can deliver the CubeSat into different orbits in a single mission. So to deploy, to send the CubeSat into the lunar orbits, we choose the Momentus transfer vehicle that is compatible with most launches, or we can also choose the Rocket Lab photon transfer vehicle as well. Next, please. So the EDR design is quite different than the CDR design because it is for the actual space mission, and we have the philosophy of reducing mechanical parts in it. Next, please. This is the cost budget of the actual CubeSat. As you can see, the whole CubeSat is around $800,000. We have some estimations on components that didn't give us any quotes. Then, including the launch cost, the total cost is around $900,000. Next, please. And this is the mass budget of the CubeSat. The total mass is around 4.8 kilograms. With the 6 kilograms limit, we have around 20% margin, which is acceptable at this stage. Next, please.
We tried to use the design of the components to reduce design and validation time as much as possible. This way, a higher reliability would be achieved because of the high readiness level of the TRL technology. Almost all of the components have flight heritage, which also adds up to the reliability of the design. 3 sides of our satellite would be covered by solar panels, as well as the top and bottom surfaces. The top shelf would contain the batteries, the middle shelf, the cameras, and the reaction wheel and propulsion system would be placed at the bottom shelf. 6 sun sensors and star trackers would be placed all around it as well. Next, please. Payload-wise, the ISIS onboard computer was selected. It has a high memory, lightweight, and a high processing capability. A SD card would be used for extra and backup storage. This computer is compliant with CubeSat standards, as well as having multiple general purposes pins, which is ideal for the connection with the sensors. Next, please. The selected camera is the Mantis imager, as it has a high resolution and fits a 1U volume with a low power usage. Next, please. Our science radio receiver was the ISIS full duplex transceiver, which has a high flight heritage and a flexible configuration on request, perfect to meet the requirements. Next, please. As I mentioned before, our design included 6 star trackers because of redundancy. Those have a compact design and a lightweight, as well as a fairly accuracy. Next, please. And we also use 6 sun sensors, again, because of redundancy. Next, please. Our IMU included 3 linear accelerometers, 3 gyros, and 3 inclinometers. It has a high resolution and accuracy and flight heritage, and its integrated controller and fault detection system reduces the main computer workload. Next, please.
So as we are no longer constrained to a single rotational axis, we decided to go for a 4-reaction wheel array. So the extra 4th wheel provides redundancy in the case of failure, but during normal operation, we have larger momentum storage. So this would delay saturation during mission time. And the unit also has a pre-designed bracket, so this means you can integrate it easier into our CubeSat. Next slide, please. Again, the thrusters have an integrated controller, reducing the workload on our computer. The propellant tank is adjustable, so this means we could use different configurations. For example, if we needed more delta V for deorbiting in an end-of-life cycle, for example. And this also uses cold gas, so this complies with the regulations on hazardous or toxic components during the competition. Next, please. So our S-band radio operates at 2 frequency bands, so this covers the entire range of the transmission and receiving requirements. And again, this is a highly configurable component, so we can adjust for frequency ranges, data rates, and transmission power depending on requirements. So for example, if we need to lower our power usage. Next, please. Here's a very simple link budget for our CubeSat. So this estimates the received power at the relay station, gives us a good idea of where we will incur losses, and it shows us that we're always destined to get a large and significant loss due to the free space between our 2 satellites. Next, please. And finally, we've changed the structure from aluminium sheet metal to an off-the-shelf component. So this is lightweight. This is useful because, as we saw earlier, our margins on mass will become much tighter than our CDR. And this is also compatible with a lot of consumer solar panels, so it means easy integration once again. Next, please.
So the solar panels that we are using are from the same company as the CubeSat structure. That's because it's easier to integrate it on the structure itself. And we have 2 types of solar panels, one which is a 3U size. It has a voltage output of power output of 8 watt, and a smaller one, the 1U size, which has a power outage of 2.3 watt, which is placed on the top and bottom of the CubeSat. Next, please. So the batteries that we are using is the 350 watt-hour high energy density battery. To size the battery, we use a 1 orbit time, which is 2 hours as a benchmark, and the power usage we've calculated is around 100 watt-hour. So this battery can provide 3.5 orbits time of full power usage for the CubeSat. Next, please. And at last, for the heating, to keep everything, all the components in the CubeSat within its operation temperature range, we will use the custom designed carbon fiber channel radiator. It is actually designed by NASA, and we chose this design for the low power usage and the compact design. Next, please. So this is a table for the power budget. We have 4 columns for analysis. The first one is the peak power usage, which is around 64 watt. Then in the normal operation, it uses only about 50 watts. And when it's charging, it uses 3.5 watt. And there's a net charging of 4.5 watt when only one 3U solar panel is charging. Next, please. And the whole operation will be split into 5 phases. The first one is the before mission phase, which starts from the launch of the CubeSat to when it is deployed in the lunar orbit. Then it is the calibration phase, where the radio will be turned on and communicate with the relay satellite and send signals back to Earth. And then the solar panels will charge the batteries, and all the sensors and payload will calibrate itself. Then the actual 3-month mission phase will start. The CubeSat will automatically capture photos and radio signals from the lunar surface and send the data back to the ground station through the relay satellite. After the 3 months, it will be the extended lifetime phase, where the CubeSat will operate until it is broken, or the ground station commands it to end itself, then it will enter the end of life phase, where the CubeSat will ignite its cold gas thrusters and perform a deceleration burn to impact the lunar surface. Next, please. So the end of life operation, it's a retrograde burn from 100 kilometers altitude to 0. The delta V required for this operation is around 23 meters per second, and the minimum delta V is 21 to hit the tallest mountain on the moon. But the problem with the current design is the propulsion system can only deliver 8.8 meters per second. So we will require a larger propellant tank. Next, please. And this is the list of the tests that we will do if we are actually building the CubeSat. Next, please. To conclude, a 3U CubeSat lunar mission is feasible, but a larger platform like a 6U is more desirable because the major constraint is the volume. So the mass is under the limit with 20% margin at this stage, which is acceptable. There are a few changes to the design that we will need to do. So the first one is we will design a smaller reaction wheel package. The current one is too large and over-designed. We will need a larger propulsion system for the end-of-life operation. The current one's delta V is not enough. And we can design extra deployable solar panels for quicker recharge time and longer continuous mission time. And the current design relies on a relay satellite to transmit data back and forth from the ground station. So we are most proud of being able to achieve 2 CubeSat designs in a year, even though the team haven't even met once. And everyone in the team, more than 70% of the team members are first-year students. So we are really proud of that. And thank you very much. Next slide. Yeah, thank you very much.
Thank you very much, Bristol.
Excellent work, guys.
I will jump in right away with some questions. We're just a little tight on time, so we'll rattle through them very quickly. My first one would be, did you work out what your footprint size was?
Sorry, what was that?
Did you work out what your footprint size was when you're actually observing? Excuse me.
The footprint size.
Yes. So whenever you're observing, I think for your EDR, you said your altitude was 100 kilometers.
Yes. Yes.
Yeah. So for how long? I mean, you can look at this in 2 ways. How long are you observing landmarks for? Or how much can you see of the moon's surface? Have you looked at that?
Do you mean the how long we can see the moon surface? We can see the moon surface.
Sorry, no, as in a landmark, a particular landmark on the moon surface. So once that comes into view, how long can you observe that for?
Yeah, we've calculated it. It's about, I think, I don't remember the actual number, but around 10 minutes.
Okay. Because I mean, in terms of how if you wanted to work it out, or if you have already, because I'm just thinking, with the field of view of what you have on board, and 100-kilometer altitude, obviously you want to make sure that you're observing for long enough as you actually go around. So I was just wondering, because field of view time, if you're orbiting at 2 kilometers a second,
yes,
at 100 kilometers altitude, it's just a consideration, I guess. But that, I'm not pressing you for exact values. I'm just wondering, have you considered it?
We have considered it, but the payload, the reason we chose that camera is we want a high resolution image of the landmarks. So
cool.
Yeah.
Okay, thank you.
My time to jump in, I guess. First off, well done. I thought it was really good, really great to see. Couple of questions from me about you mentioned the link budget. I just wondered if you had sort of a data rate or a plan of how large these images would be and maybe how long they'd take to get back.
I don't think we had values for sort of the sizes of the files that would be, or the size of the data we'd be transmitting, but we did have data rates that the components were capable of, but I don't think we went into the depth of calculating exactly what we would get. We were already using a lot of assumptions in the link budget, and it got to a point where I was doing calculations where I pretty much only knew a couple of the variables. I thought I wouldn't give an accurate enough reading to be worth anything. So no. So,
that's okay. That's okay. And you also touched on your reaction control system reaching saturation at some point. I wondered if you'd thought how you could deal with that, or if you knew when that point would be.
Yes. The EDR design, the reaction wheel, has a really large momentum storage, so that will delay the time that is needed. And the propulsion system that we have, the FACU CUSB1, it has 4 cold gas thrusters, so it is able to rotate the CubeSat in one angle, one axis of rotation. So that would be used to desaturate. Yeah.
Okay. Thanks very much. Well done.
Cool. David, do you know if there are any other questions coming in, or can I squeeze one last one in?
Yeah, you can squeeze one last one in, I think.
Okay. This is a little link to link budget as well. I was just wondering, have you got, is your observation always on? Like, are you observing, taking images at all times?
We will try to maximize the time we take the image until either the memory is full or the power is low and we need to recharge.
Okay. So are you taking it as a full? You want full high-res images of the entire lunar surface? That's what you want.
Well, if the mission dictates a high resolution of the lunar surface, we can scan the whole lunar surface and then save the data in the memory storage and send it back to the ground station. So yeah, we can adjust the mission to anything.
Yeah.
Yeah.
Okay. Yeah. It was building on from Phillips of if you've got all the high resolution images going.
There are 2 modes for the camera. So there's a lower resolution, but a bigger field of view, or a higher resolution, smaller field of view mode.
Okay.
So yeah, we can change it.
Cool. Okay. That's all from me. I think that was an excellent presentation. Yeah.
Thank you very much. Thank you, Bristol. That's been a really good presentation, and thank you for answering all the questions and things. And yeah, I hope you've enjoyed it, and I hope you enjoyed the competition and everything so far. But yeah, okay. Thank you, Bristol. We'll probably go to a short break now, and then we'll be coming back with UCL's presentation in a minute.
Thank you.
Okay, welcome back again, everyone. Sorry again for being slightly off schedule, but we'll hope to get back on as soon as we possibly can. But we're now joined by Team Vestigo. I can't remember if I'm saying that properly, from UCL, who will be sharing their design with us. Again, they are in the EDR side of the competition, as we discussed earlier. So I'll hand over now to the UCL team. So thank you very much.
Cool. So hi everyone, we're Team Vestigo from UCL, and like David said, we're going to be presenting our initial CDR design and then EDR design. So first we'll run you through the overall mission objectives, and then we'll work through CDR first and finally the CDR. So the overarching mission aim was to provide a cheap 3U platform for imaging specific landmarks on the surface of the moon. And we focused our efforts on keeping a simple design to minimize errors and points of failure. And we also tried to maximize revisit times and try to incorporate a sustainable disposal mechanism as part of our mission. And overall, we feel like we've taken this to test readiness level 4 to 5. So now Mariam will run you through the CDR spacecraft design.
So to comply with the CDR requirements for our design, we have 4 main components. So first is the thermal non-contact sensor. This was to detect thermal objects of interest between the range of -25 to 100 degrees Celsius. Next, we have the infrared spectrometer. This is to detect waves within a region of 410 to 940 microns. Next, we have an optical lens with 12 megapixels to collect images of the landmarks of interest. And finally, we have an EMF radio receiver with a frequency range of 915 to 921 megahertz. And this is to detect signals and ultimately communicate data from the onboard computer. So these components would have fulfilled the requirements for the simulated lunar environment and also complied with the CubeSat budgets that we had in place.
So the model on the left shows the proportions and segments of the CubeSat design, and the model on the right shows the interior arrangement of the components. So there's 3 regions: the payload segment 1, payload segment 2, and the platform segment. So platform segment has the onboard computer in it, battery, receiver, and wiring. The bottom segment has the reaction wheel in it, and the top segment has all the scientific instruments. So for the onboard computer, we selected a Raspberry Pi compute module, version 4, which requires a quite large I/O board in order to expand the interfaces to accommodate all the sensors. So we actually mounted it vertically on the center diagonal of the CubeSat. So that's item number 4 and 5. Number 10 is the battery. That battery is just taken from a drone, and we're mounting the the I/O board using 3D printed screw mounts inside the frame. So in payload segment 1 at the top, we've got the infrared spectrometers, 3 of them arranged in a crescent. That's item number 1. And then we have 2 optical cameras, which is item number 2, and then 1 infrared sensor, which is item number 7. And the reaction rails is item 8 and 9. And there's also a hook attachment point number 11, which was specified in the requirements for the competition.
So for the attitude control system, we also tried to keep things quite simple. So the aim was just to rotate the CubeSat around a single axis to allow us to collect as much data as possible on all the information around us. And we wanted to be able to do this with an accuracy of plus or minus 5 degrees. And we were kind of interested in trying to 3D print some components at the time. So because we had enough volume in the CubeSat, that wasn't really much of a limitation. We decided to 3D print it out of plastic and then add some metal ball bearings in it just to increase the inertia. And we tested this on an Arduino board, and it was good enough.
So during lockdown, obviously, we're unable to meet as a team or use laboratories in the university, but we did manage to do some small-scale prototyping in our homes. So we obviously already seen the reaction wheel, but we also 3D printed a scale model of the frame of the CubeSat, and also got a few of the scientific sensors, such as the spectrometer and the cameras, connected to a Raspberry Pi Model 4B, which is basically identical to Compute Module 4. And we ran some simple code to stream data from these instruments to a laptop, as we would have to do in the mystery room.
Okay, so now we'll run you through our EDR. So I think Jennifer will present the mission.
So going now from the mystery room prototype to an actual CubeSat for the EDR, of course, quite a few changes have to be made. First of all, we actually need a mission plan and, well, all in all, much more extensive planning. So first of all, the satellite has to be built, and we expect for the build to take about 2 weeks, and most of it should be, most of the work should be taken out at the Mullard Space Science Laboratory, which belongs to UCL, and first of all allows us to cut down on cost of quite a few of the parts. And furthermore, MSSL provides all the testing facilities we need to guarantee a successful mission. So we will run the CubeSat through vibration and acoustic testing. The code itself has to be tested extensively. And we have a vacuum and thermal testing. And once it hopefully successfully absorbs all the testing, the CubeSat can then be shipped to the launch provider and prepared for launch. Once it has launched, it will take around 3 months until it is finally in the lunar orbit where we want to have it. So we need about at least 4 months before we can actually gather data to start with the build. Once the satellite then gets ejected after it's transferred to low lunar orbit, it is not in a, stable position. It's still tumbling. So first of all, we have to stabilize it with the ADCS. And only then we can actually turn on the CubeSat and check whether the systems are working. This is done by, direct telemetry with the ground station. And only once we deem the satellite healthy, we can start the main mission phase, which is first of all set for 3 months with a probable or possible extension afterwards.
In terms of launch and orbit selection for our satellites, we've decided we're going to be hitching a ride with companies such as Rocket Lab because they offer dedicated launches of CubeSats on P-pods. So this would give us more leeway on determining our launch window as well as optimizing the launch for our specific orbit. So ideally, the CubeSat would be launched into orbit using a 3-stage Electron rocket into low Earth orbit, after which the Photon kick stage will separate from the main stage vehicle and perform a translunar injection burn to get us into our desired orbit. So when it came to selecting that orbit, we've optimized it to maximize flyover time over the selected landmarks. And we found that at 363 kilometers altitude, we could stay within a reasonable thermal exposure range, as well as reach the optimum distance for our optical sensors to work at the required resolution. So with these orbital parameters, we're going to be passing over 9 out of 10 landmarks during the mission, and we would have about 100 to 300 hours of flyover to collect the necessary data within the 90 days.
Once these 90 days are over, or possibly even after the extension of the mission, we will have to consider how to get the satellite back such that it doesn't pollute the vicinity of the moon. Around the Earth, this is usually done by having the satellite come back into a lower orbit and finally burn up in the atmosphere. However, due to the moon's lack of atmosphere, this is not possible. However, as the moon is not populated, it is not problematic to just have the CubeSat crash onto the lunar surface. And this is actually helped with by the composition of the moon. The moon's mass is very unevenly distributed. And as you can see on the bottom right corner, that leads to strong gravitational anomalies. And basically every but 4 very distinct orbits around the moon are inherently unstable and will become chaotic in a matter of a few weeks to a few months. So if we, during our mission time, we can stabilize the orbit of our CubeSat, and afterwards it will inherently crash into the moon. If we still have thruster power left, we can actually give it a little shove and just select the landing site. But even should we run into unforeseen problems and lose control to the CubeSat, it will crash eventually onto the lunar surface and not pollute the space around the moon.
As per the requirements, the CubeSat will communicate with ground stations on Earth through a relay satellite. The table on the left shows the coverage time, the graph on the left, sorry, shows the coverage time available to the lunar relay satellite during the first month of operations, calculated using OpenCosmos. On average, we will have 700 minutes of coverage time per day to downlink data and uplink commands to the CubeSat. Most of the time will be used to downlink data, but the first 5 minutes of each communication window each day will be reserved for spacecraft software updates and maintenance. The tables on the right summarize the data packet structure for dayside and nightside operations. On the dayside, 2 visible and 2 IR images will be taken over a 2-second period, while on the night side, 25 IR images will be taken in quick succession. Each data packet will be 26 megabytes in size and include imaging and ephemeris data, taking around 1 minute to downlink to the relay satellite. In addition, the CubeSat has 3 gigabytes of internal storage, meaning that 115 packets can be stored on board if the need arises.
So for designing of this lunar mission, we had a significant increase in the budget to about £10,000 and some changes to the mission requirements. It's just showing some of the components that were added for the design for the EDR after reevaluating the selections we made for the CDR. So the aim was to keep the CubeSat design as simple as possible and as reliable as possible. Obviously, all these components were selected within the budget, volume, and power and mass constraints. So the Raspberry Pi Compute Module 4 was replaced with Raspberry Pi Module 4B because it takes up less volume, and the newer models have various modes of reduced power consumption that you can switch between. We also include a GPIO extending board, so we get double the amount of GPIO connections, which allows us to have redundant photosensors and gyroscopes. We selected the Arduino cam because it has motorized lenses, so you can automatically focus, and you can get infrared versions as well, so we can use the same hardware for infrared and optical. With a GSD ground sampling distance of less than 1, basically that means that we can resolve in 1 pixel an object less than 1 meter in diameter. We also use 1 static solar panel and electrical power system that are both capable of heating themselves and recording their own temperature, and the APS is able to reactivate automatically if it unexpectedly loses power. And the deployable antenna is just selected to meet the requirements of the relay satellite and link budget. So on the left, that's a very simplified state hierarchy of our CubeSat. And on the right is the subsystem layout for the onboard computer. It's not showing all the components, but it's showing the main ones. So during initialization mode, the CubeSat performs a number of checks and synchronizations of sensors before moving into the engineering and science modes, which include substates for attitude determination, data relaying, cruising, charging, and imaging. There's also maintenance routines under this header, which for software updates and detumbling and minor attitude adjustments. Safe mode is used when we require a significant amount of power, or the majority of power, to be sent to the propulsion systems or the attitude correction, and so it just deactivates all the imaging and the sensors.
You're muted, Gabriel.
Sorry about that. Unlike its low Earth orbit-based counterparts, the CubeSat will operate outside the protection of Earth's magnetosphere, where it will be exposed to large doses of ionizing radiation from galactic cosmic rays, or GCRs, and solar energetic particles, or SEPs. The SPENVIS program was used to model the lunar radiation environment for the duration of the mission. The predicted mission average GCR and SEP fluxes were then input into the molasses program to determine the optimum shielding configuration for the CubeSat. The figure on the left shows a dose depth curve for a silicon detector behind an aluminium slab of varying thickness. The dotted line at the top of the graph represents a maximum safe radiation dose for the Raspberry Pi OBC. We can see that the industry standard 2mm aluminium shielding is already sufficient to reduce the mission absorbed dose to 4 orders of magnitude below the maximum safe dose for the OBC. The margin of safety offered by the shield will also greatly diminish the threat from intense SCP events that can cause short-lived spikes in the absorbed dose rate. The figure on the top right shows the external structure of the CubeSat, including the aluminium shielding, solar panel, and antenna. While the figure on the bottom right shows its internal structure. The internal structure was kept largely the same from the CDR, except for the addition of a camera turntable mechanism and an enlarged enclosure for the reaction wheels. When the cameras are in operation, they are rotated into a position where they can see through 2 cutouts at the base of the CubeSat structure. At other times, they are rotated into a position behind the shielding to minimize their exposure to radiation.
Okay, so for the attitude and orbit control systems, we identified this as a relatively high-risk aspect of the mission, somewhere where we could potentially extend the mission lifetime and also make use of it to sustainably dispose of our spacecraft. So overall, we felt like we needed around 50 meters per second of delta V budget, and we could provide this with some off-the-shelf cold gas thrusters, and then we could provide enough torque to do 360-degree rotation on any axes with 3 reaction wheels, and the cold gas thrusters would give enough thrust to spin them up and off as we needed, and they'd also allow for just general station keeping. So overall, the mission risks were mitigated using a mission risk table. So every week when we met, we just kind of went through, added our mission risks, saw what we could do to mitigate them in terms of design, and tried to incorporate that at every stage. And similarly, with our requirements matrix, we kind of tried to see how we could meet them, which ones were higher priority for us, whether they were compliant or not, and how we were going to ensure that they were compliant throughout. And finally, to tackle our project risks, we used a project tracker. So we just kind of assigned all our tasks, subtasks, assigned them to people, gave them dates, and then on a weekly basis, just tackled them and kind of rearranged them if we needed to. And similarly with our budgets table, we wanted to obviously stay within the requirements of power, volume, cost. So we just stacked those up weekly and just did some rejigging of things where needed. And that's it for us. So thank you very much.
Thank you very much. I thought it was a really good presentation. Just clearly you've put a lot of work into it over the course of the year, and it's great to see. Do we have, first of all, any questions from the judges?
I'll go first. Great job again as well, team. That was really good. My main burning question was about the solar panel. Did you just have the one on one side?
Yeah, just the one.
So I guess that puts. Did you consider sort of how that would affect your attitude control? Because if you lost that pointing, then that would be quite serious. So I guess what made you just choose the one for that?
There's mainly budget constraints. we're very keen to keep it below £10,000, and space grade solar panels are really, really expensive. So we would have regular attitude adjustments to try and keep that pointed in the most optimum direction. But it basically means for every 10 cycles of charging, we can only really have about one of imaging.
Okay. And I guess you'll have to point in a certain way to take your images. I guess the panel looked like it was on a different axis to that, but would you be able to take images while still pointing the solar panel towards the sun, do you think?
I think that possibly, but I think probably have to be solely on the discharge of the battery when we're imaging.
Okay. Thanks for that.
Okay. I'd just like to kind of interject here quickly, sorry, Alex, and just say to the audience that if you want to ask a question, it can be technical or it can be non-technical, then use the Q&A box below, and then I'll read them out. I've got some to read out, but yeah, if you go, Alex.
Well, my main question was actually going to be the same as Phil's, which was, if you've only got one solar panel, how can you point at both the sun and the surface of the Earth or surface of the moon when necessary? And I think you were correct in your answer, which is you can't at all times. I guess, so a question I wrote down, and you have sort of answered as well in your presentation, not beforehand, was, well, with the requirements, what were you taking as maximized revisit times? Because there is ambiguous language with that, and I get that. So what did you take as meeting the requirement of maximize revisit times?
So initially, I think when we were doing the mission design, we just thought the bare minimum would be to get one image of each site in optical and IR, and then we just worked to just add as many as we could on top of that.
Okay, because you'd said about I'm trying to think which word was actually used to describe it, because certainly in terms of revisit is typically the time between observations, but I believe you said you wanted to maximize how long you were observing for of a landmark, which is again slightly different from what you said about meeting, because you're talking about revisit in terms of revisiting multiple times. Was that your main goal, or was your main goal the length of that observation?
I think we tried to maximize for time over each site. So
okay,
yeah, in hours, how much time would we spend with each site under the actual sensor itself? Okay,
yeah, because with a circular orbit, you can't you will see every site the same amount of time. And so there's obviously a difference between looking at a site for a long time and visiting a site more frequently, which can still be used to see it more, but it's whether you want to do it in a single bucket or multiple buckets. Okay, so yeah, that was all for me. I thought I will say I liked there was a good systems engineering approach, and I do like that. So yeah, I thought that was very good.
Yeah, I thought the way that you assigned the tasks was really good. That was good to see.
Thank you, judges. Thank you for the questions. We've had a couple of questions that have come in, just general questions. So, what was the hardest part of adapting your mission? I don't know. It's a bit of an open-ended one, that, but
I guess, I mean, I don't know if anyone else wants to take this, but I guess changing the actual requirements from Mystery Room to Lunar and trying to keep what we understood in the first design, all the like lessons we learned, and try to carry those forward into the second one and not just bin all of that and start anew. Yeah. And I think dealing with, the difference between space grade and Earth grade and the radiation and thermal fluctuations and stuff.
I think something else that should also be mentioned is that we also never really met, and we had exams at the time and people were just starting their PhD. And so that was actually quite challenging. But I think we mitigated that quite well by also having like a relatively strict schedule and advising different parts of the problem to different people. But I felt like that was definitely hindering and definitely difficult.
Definitely, it's been a very challenging year, I think, and it's unfortunate that we've had to. We all thought we'd be able to build at the end of the year, and then we've had to go back, and no one's really been allowed in, which is such a shame. So I've had another question, which is slightly lighter. What was the most rewarding part for you of the whole competition so far?
Well, I guess Gabriel was kind of joking about it earlier when we were having a chat, but I guess the friendships you make. We were just saying if this goes horribly wrong, at least we've made some good friends.
Mate, I wasn't serious about that, you know.
Yeah, I think meeting like-minded people who are just kind of like keen to do space things outside of their curriculum and that are just, you know, happy to just chat about satellites for an hour. It was very nice, yeah.
Okay, no, that's good. That's good to hear. You have a question, Alex?
Yeah, based on the fact that you weren't meeting each other, you're having difficulty with that, and I noticed at the start, certainly from the people presenting, you're astrophysicists and you're civil engineers. So how did you find what you've previously done in courses and stuff carried over to this? Or did it?
I haven't done anything like this before, to be honest. But
same here. There's very little overlap with my main project.
I found it actually quite funny because, I mean, as a physicist, it helps. You have like some thermodynamics knowledge, so you have to like, okay, you're going around the moon. There might be this and this and this difficulty, but then again, if it all's down to the engineering, and then you just like go on the web and Google like CubeSat main parts or something, and you just go from that. And I think that worked well, which I found very impressive because I had no clue whatsoever at the start.
There's also that most of us working on PhD projects are attached to a existing spacecraft mission. So we can draw a bit of expertise from our projects and from our supervisors and apply it onto this CubeSat competition.
That's interesting. So did you find that it kind of benefited in a way to have people from different backgrounds to kind of have a different perspective on things? Or
well, yes, diversity of ideas is always helpful. It's always very beneficial. Because otherwise, you just get tunnel vision. You just get fixed on one certain way of doing things, and maybe that way of doing things isn't the best.
That's very interesting. No, it's good. You're a very diverse team, and it's nice to see that. So that's good. Okay. Do we have any other questions from our judges?
I think that's me. I'm all done.
Yep, I'm happy with that. Well done.
Okay. Cool. Thank you very much. And yeah, congratulations. That was a great presentation. Yeah, look forward to seeing you again, hopefully in the future in competitions. So thank you very much.
Thanks.
Thank you.
All the best.
Thank you.
Okay, welcome back everyone. Thank you for joining us again. Sorry we've had to kind of miss out on the 15-minute break, but we're now back on schedule, so it should all be okay. So we're now joined by the University of Leicester SatX team, who will be presenting their mission as well. So they were also on the EDR side of the competition. Yeah, so we're looking forward to seeing what you have to say. And feel free to ask any questions throughout the presentation from the audience using the box below. So thank you, Leicester.
Respected judges, honorable guests, and my dear friends, good afternoon. My name is Mohammed, and today my team and I are going to present our work within the satellite design competition. So without further ado, let's begin. In this presentation, we're going to look at an introduction to the team and the mission. Following that, we will explore our work within the preliminary and critical design stages. Next, we will discover the adaptations that have been made before finally looking into the extended design, beyond which we will conclude the presentation. Introduction. Our team is called SatX team, and we're a team of 4 active members. We're all first and second year undergraduate students studying at the University of Leicester. We're all passionate about engineering, design, and space. Our CubeSat is called Nifty Fridge 1. This is because the early prototype design looked a lot like a small fridge. Mission statement. Our mission is to design a CubeSat that will be launched into lunar orbit to detect, identify, analyze, and relay information about the targeted lunar landmarks. The mission has been split into 2 stages. The preliminary and critical design stages have been focused on a simulated lunar environment, whereas the extended design stage has been focused on an actual lunar environment. Mission requirements. We've been given a mass budget of 6 kg and a volume constraint of 3U. The mission requires us to design our own power system, utilize legal frequencies, ensure that the satellite is fully operational remotely while also planning the ConOps. Similarly, we are required to run some simulations for validation and, of course, maintain environmental and safety conditions. This is our project roadmap. We have been working on the mission for 9 months now, starting in December 2020, and we have successfully completed various design and development stages along the way. Let's look at our work within the preliminary and critical design stages. This is an overview of the features and the functionality of our CubeSat. The satellite has been fully modeled on SolidWorks. Various subsystems have been integrated within the CubeSat, making the satellite capable of identifying objects of interest, thermal sources, light sources, and EM signals. Now let's explore our design process. Initial prototype. Our final CAT model has been achieved through many revisions and evolutions. From our very first prototype designed in December, the CubeSat evolved morphologically with modifications to the volume, structure, mechanisms, and much more, resulting in a final fully optimized model. One of our greatest innovations within this project has been the choice of material. We have decided to opt for hardwood plywood because it was economical, sustainable, lightweight, and was more than adequate for a simulated lunar environment. The mechanical subsystem. The role of the mechanical subsystem is to rotate the sensors placed atop the CubeSat. Furthermore, the mechanical subsystem is responsible for switching the field of view. As you can see below, the internal rotational mechanism allows rotation via a servo motor to provide a full 360-degree coverage, whereas the retractable mechanism allows a top and surrounding field of view for the sensors.
Now we will talk about how the remote sensing system fits the requirements of identifying and analyzing the sources across the mystery room. First, we have chosen the Pioneer camera. It's our main sensor, which will enable us to view both sources in the visible and partially in the infrared spectrum, allowing access to also low visibility of some sources in the room. This also allows us to synchronize with the other sensors, as it can provide a live feed of the mystery room and will give us an efficient idea of where and when we can utilize our sensors. The camera, along with the other sensors, is compatible with the Raspberry Pi, our main microcontroller, which gives perfect integration and minimizes failures of software. To the other side, we have Adafruit's thermal camera, and this also is well integrated with the Raspberry Pi and will be able to determine the temperatures of the thermal sources in the mystery room. Specific data on the objects will be available as the camera will be returning to us 768 individual infrared temperature readings and has an option of a wide-angle vision and also covers the required temperature range. In the next slide, we can see our other sensors. We start with the spectrometer, and our other sensor is to fulfill the requirement of detecting light sources with ranging wavelength and intensity as well. We had a minor challenge in this part as we could have chosen an external spectrometer device, but we decided to stick with this one, also due to its size, its weight, and compatibility and possibility of soft shooting when put in practice. We decided in finding the spectrometer by Adafruit, and it will allow us to give exact information of sources wavelength of light detected with its multi-channel feature. Next, we have our transceiver, which will be covering sources with incoming electromagnetic signals from 915 to 921 megahertz. This chosen 950 megahertz transmission and reception bonnet is able to complete this requirement for us. In this section, we also had some challenge in finding a dedicated receiver to cover this range. Finally, we have our mini LIDAR. It's our final sensor, and it will be able to detect where objects are placed in this mystery room to 1 to 5 meters away from the CubeSat. We've chosen to reside with this technology as it will be able to use a focused light and sensors to detect the range and reflectivity. So it will do this by sending a focused beam of light to the remote object, which is then reflected back to the sensor and allows us to know the distance of the object by calculating the travel time of the light beam. In this section, we also had an idea of using an ultrasonic sensor instead, but the choice was not made as it has a shorter range. It wouldn't work well with materials that would absorb the sound waves as well. Hence, we decided with this one. Next, we have the power and electrical subsystem. On the next slide, you can see a big table, which is proof of our calculations of the total power needed to power the Raspberry Pi, the sensors, and then the mechanical components, which were presented before. On the highlighted table, we have determined the total power and given a system contingency instead of giving an independent margin to all the components, since we overestimated of its nominal current of the mix of them. We thus decided with a lithium-ion based battery, which for half an hour in the mystery room can provide at least 56 watts, which is over what we need. We had this small issue that our Pi and the degree retractor have different power requirements. So since they have to be connected individually to the power source, we were in need to reduce the voltage output to the Pi, but maintain enough current to the retractor. We calculated the power dissipated by the board and the retractor, and the large amount of heat enabled us to pick a switching regulator in the end, or similarly called a buck-boost converter. And furthermore, in order to safely cut off power from the payload, we'll be using a slight switch JST adapter that will not damage the sensors and components when put to use. The next slide shows a simple pin layout of the Raspberry Pi 4B model, which is the microcontroller that we're using, and where all the components and payload will be connected. We have added a pin extension that will provide us with double the amount of these GPIO pins, as we will be using the integrated circuit, which will allow multiple sensors to be connected to the same pin, while using a unique I2C address for the microcontroller to distinguish between them. Here we have the communication system and how we'll be able to transfer our data from the mystery room to the control room. We'll be having an SD card as a safety measure to store the transmitted data. Therefore, the images, the videos, the EM signals, and more. That's a quick representation of the organization. And in the next slide, we conclude how our data will be transmitted, how our components are powered, the payload, and how the mechanical system will rotate the plate of the sensors, which will allow us to identify all the sources in the room, and overall the system integration of our CubeSat. Finally, we have the attitude and orbit control system. This will, in this part, we need to determine the elevation from the ground of the sources and the azimuth angle, which is in reference from the light source of the objects. In these images, these sequence of images show the CubeSat when identifying sources from all possible degrees of rotation, while also looking at those on the ceiling and those on the bottom of the satellite. This was being able to done since we easily mounted the same sensors on the bottom of the satellite. To determine the azimuth angle, we will be taking advantage of the servo motor and the commands that we give to it. The main light source technically will be calibrated as the 0th degree of the servo motor's rotation. Therefore, following it, any commands fed to the computer via the microcontroller would alter the rotational angle, which would correspond to the azimuth. So the angle spun by the servo motor will be the reference angle relative to the light source. We don't want to override any sensors when we give these angle increments, so we will be implementing manual signals that will use different frequencies and duty cycles. This next slide is just proof part of the code, which uses various commands to enable finding our azimuth. So altogether, we can use these commands combined to manually control the speed. We create certain loops of commands for the desired increments, and thus being able to find a reference angle for any of the objects in the room. And to finalize this section, we will be using the same LiDAR sensor as before to determine the elevation of the objects. We will do this by using the LiDAR sensor, as it can determine the object and the elevation angle, which will be calculated using Pythagorean's theorem and simple trigonometry.
CircuitPython is Adafruit's open source software which can easily integrate the Raspberry Pi and payload sensors to gather, load, store, and analyze data. We also used a systems toolkit which allowed us to analyze and visualize orbits for the lunar mission and the trajectory design. This software helps us maximize revisiting times of historical landmarks on the moon.
Environment and safety. We have focused a lot on the environment during our project. Using wood as our primary material has allowed us to contribute to sustainability. Wood is renewable and offers a very low carbon footprint, and therefore we have been able to save 3 kilograms of carbon dioxide emissions. We have also implemented a strict no plastic policy, as plastic is harmful for the environment. Subsequently, we have considered the design for environment aspects while designing our CubeSat. When it comes to safety, we have been very keen on maintaining standards, in particular to fire and electrical safety. Simulation. Since we haven't been able to manufacture the CubeSat due to COVID restrictions, we decided to run a finite element stress and strain analysis to ensure that our model is able to withstand the applied forces. A fixed geometry was selected and a total normal force is applied. A mesh was created and the results were computed and displayed that our structure was within the stress and strain limits and would not fracture.
In the CDR stage, we designed a satellite for the mystery room. The satellite would be in operation for 30 minutes. We allocated most of this time to data gathering by the sensors. A 5% marginal uncertainty has been taken into account for components with an undetermined price or weight. In the CDR, mechanical structure accounted for most of the mass at 66%. The new satellite was designed for a lunar mission, and as such, design choices have changed. These changes include a new model with a propulsion system, a solar array, a deorbit mechanism, amongst other changes. The material has also changed from wood to aluminium. The simulated lunar mission using the systems toolkit showed a successful mission both in the CDR and EDR stages. The longer the mission, the higher the number of revisits to each landmark. In the CDR stage, there were 5 revisits on average to each of the landmarks, whereas in the EDR stage, there were 110 revisits on average. In the CDR, we were unable to conduct a full orbit with a duration of 24 hours due to the inaccessibility of software features. This was resolved in the EDR stage because STK launched a software update. As a result, we were able to set a longer orbit. For launch surfaces, we opted for a space flight launch surfaces, which would launch the CubeSat to low Earth orbit. This was an economically viable option. The advantage of the deployer include the no use of pyrotechnics in pyrotechnic actuation, and no debris release during actuation, among other advantages.
Let's look at our final extended design in a bit more detail. Our CubeSat had to be modified and revamped to account for an actual lunar environment. Let's explore the changes that have been made. Mechanical subsystem. We have decided to opt for a ready-made 3U bus structure manufactured by Sat Revolution. The reason we chose this product was because it was made out of aluminum 6061T6 alloy, was lightweight, and was tested for thermal vacuum and random vibration. Speaking of vibration, the launch is a major source of vibration and affects internal systems. Therefore, we have decided to opt for high vibrational dampening parts to minimize these effects. Also, to reduce any unwanted reflections and to increase the efficiency of the optical system, we have decided to black coat our optomechanical components for improved optical performance.
Now we look back at the remote sensing subsystem, this time for the EDR. In order to satisfy the requirement of observing the lunar surface and its landmarks from a low Earth orbit above the moon, a camera system would be implemented. First, we have the main camera to the left. It's a high-resolution camera that features a wide-angle lens as well, and also high shutter speed settings. This CubeSat camera has also proven test flight heritage from previous missions as well. And further analyzing will be made with infrared technology, as it can allow greater detail to complete that data of the surface of the lunar surface. And the camera chosen for this is also small, lightweight, and has undergone more than a dozen missions before. In addition to the cameras, spectrometer kit. This will be mounted while orbiting the moon, and it will collect data from the lunar surface below. Since the portion of the electromagnetic spectrum that will be detected by the spectrometer often be from the sunlight reflecting from the surface of the moon, in a future mission, it would be useful to look into transmitting other parts of the electromagnetic spectrum waves, which could be reflected from the moon's craters and especially closer to its poles. For the purpose of this mission, we decided this technique and this dedicated wavelength, near infrared wavelength, majorly due to its availability and adaptability. But in a future mission, it would be useful to combine spectrometers observing ultraviolet radiation, radio waves, and etc. And to the left, to the right, we can see our lidar sensor that we have chosen. We have chosen this to map the lunar surface by emitting lasers down to the moon at a known distance from the lunar surface and measure the time it takes for the lasers to return to their origin. So as the CubeSat orbits the moon, the lasers will bounce off different features of the landscape. The shorter return times will correspond to taller features, and longer return times correspond to shorter features. And this has been chosen as a leader system for the CubeSat. Our
So talking about the power subsystem, the total power required for the satellite is 122.4 watts. This is with contingency comes from the fact that different components have different power usage depending on the state that they're in. For instance, if they are idling or fully off. Two solar panels have been implemented on the satellite, as with both being able to produce 16.8 watt hours of energy. And the minimum power required for the satellite is 15.7, so the remaining power will be stored in the battery. In order to complete our mission, all of the components necessary for it will be run from the battery. Talking about the communication subsystem, the communication between the satellite and the ground station will be established via a relay satellite. This ensures that we don't need to have such powerful transmitters and receivers because the signal doesn't have to travel all the way from the satellite to Earth. Also, the transmitter and receiver systems are different entities instead of having a transceiver due to redundancy reasons. The communication system uses S-band, which is one of the most popular frequencies used for space communication, and it covers the frequency from 2 gigahertz to 4 gigahertz. One of the key features of our satellite or of our communication system is the antenna, which has a polarized beam, which allows for better communication and reduces the chances of interference.
Finally, we have the iron thrusters. We have chosen this as the main propulsion system to power our CubeSat. The propulsion system is efficient of fuel and electrical power, which will enable our satellite to travel faster, further, and cheaper than any other propulsion technology currently available. We have decided to stick with the emotional nano as our thrusters, as it is fully developed and tested. In the next slide, we can see our attitude determination control system. It's sort of a package which includes the star tracker, the gyro reaction wheel, the magnetometer, and the ability to also connect to other external sensors such as some sensors. We decided to add on precision gyroscopes to support the operation when the star tracker is blinded. Furthermore, this product will undergo acceptance tests and vibration tests as well.
The command and data handling subsystem is the brains of the satellite, controlling what the CubeSat does, when it does it, and why is it doing it. It is responsible for data operations and issuing commands. We have chosen an onboard computer manufactured by Endurosat, as it was flight-proven, efficient, robust, and had high resistance to radiation. And more importantly, it was lightweight and offered up to 32 GB of secure onboard memory.
About the environment, as all electronic components have a specific temperature that they like working at, and space is really cold, there's going to be a heater installed in the satellite. And to protect against drastic heat spikes, a heat sink is going to be installed to overcome that. Before launch, we're going to do vacuum testing to make sure that there's no air bubbles that could get trapped in the structure of the satellite and potentially damage it. In order to keep as much heat in the satellite structure as possible and to protect against potent gamma rays and space radiation, heat insulation is going to be intertwined with radiation shielding, thus allowing for a thicker layer of protection to be installed on the satellite.
In the EDR stage, the satellite was designed for a lunar mission with a duration of 4 months. This is a much more complex mission, and as such, it will take a week for the satellite to deploy, another week for the satellite to be inserted into lunar orbit. The satellite will be in orbit for 3 months, revisiting landmarks on the moon, and it will begin end-of-life operations after 3 months. A deorbit mechanism has been installed into the lunar mission satellite. The dome will deploy once the operation of the satellite is completed. All the components were known. All the components' masses were known. The cost for the payload and launch services were unknown. Payload accounted for 50% of the weight in the EDR stage satellite.
Conclusion. We believe that our CubeSat designed for a lunar mission is the most suitable approach to capture high-quality data. This has been made possible thanks to state-of-the-art technology integrated within our CubeSat. Our satellite is not only compact and lightweight, but also offers a very economical budget thanks to shorter development time and reduced launch costs. Considering all the benefits of our CubeSat platform, we would like to conclude that our CubeSat mission is worth pursuing and a larger platform would not be required. So, to summarize, in this presentation, we've looked at an introduction to the team and the mission. Following that, we explored the preliminary, critical, and extended design stages in a lot of detail. And finally, we determined the conclusion. Thank you all for watching. We hope you found this presentation informative, and we're happy to take any questions now.
Thank you very much for presenting, Lester. That was a really, really great presentation. It was really interesting to see how your design developed and was adapted. Yeah, we'll hand over to the judges first again to see if they have any questions.
Yeah, I have a question to start then. I like the way that you actually used your CAD model for something as aside to just being a CAD model. So what was sort of the thinking behind that? And using that so much?
Yeah,
for like
I'm
FEA,
happy.
for Azimuth, etc.
Exactly. I'm happy to answer that question. Since you're aware that due to the COVID restrictions, we have not been able to manufacture the CubeSat. So this is why we have decided to dedicate a lot of time and a lot of efforts towards the CAD model. It was a major part of the mission. And the reason we have designed it in a lot of detail and assembled all the components is because if we were to manufacture it, we would want to make sure that the components would fit inside and we could have a mass estimation as well. and then as we've said in the presentation, to run the finite element analysis to ensure that what we are designing is going to hold the forces applied together. So this is why the CAD has been a major focus in our mission, and we have tried to assemble every single component within it for the CDR stage.
Cool. It was really good for both models. I like as well that it was clear, that was a focus.
Yep. Well done. That was really good. Really liked seeing the wood construction for the mystery room one. That was really interesting. And actually, to circle back to what Alex said about the CAD, that's true that even Airbus themselves have been utilizing CAD models even more to help during the pandemic, because ordering things gets more tricky. In terms of my questions, I had a question about you mentioned the end of life and using drag to slow down. Could someone just clarify or give a bit more information about that?
Yeah, I'm happy to take that question. So as you know, that generally all lunar missions that are placed into orbit around the moon, when they reach the end of life, they have to crash into the moon. Okay, some of them might have some fuel left in their thrusters to have a final burn to deorbit and crash into the moon. For what we've done here is that we know that eventually our CubeSat will crash into the moon. But the focus of the deorbit mechanism was to make this process occur faster as the drag was created. So this was the main purpose that the DOM or the deorbit mechanism was applied to ensure that this process is completed faster than it would have if we weren't having that feature on our CubeSat.
I mean, obviously there's no significant atmosphere around the moon, but I get that there'll be some small fast-moving particles probably. So I guess for the mass of the system, is it really worth that trade-off? Do you think it would reduce that time significantly enough to justify carrying that for the mission?
Yes, I think so, because since we have not planned a final burn, since we assume that our lunar transfer and inserting into the orbit might cause us a very high reduction in our propellant. So this is why we have not planned any final burns for the end of life. Instead, we have thought of using the deorbit mechanism. And yes, we completely agree to what we said in the mission.
Also, just if I can slip another one in. So you had this moving head, which you can see on the mystery room one. Would that have been? Would you have that on the EDR?
Yeah, I'm happy to answer that as well. Since you're aware that the wooden CubeSat was manufactured for the mystery room, and what we have done is we have decided to remove the top ceiling to have an extended field of view for our sensors. And as you've also noticed, that we have a retractable mechanism that is able to orientate the sensors towards the top ceiling view, so we don't want to miss out any data signatures that may be there. But when it comes to the actual lunar environment in the extended design, now we have the entire the top ceiling sealed. This is also because the deorbit mechanism is placed atop the top of the CubeSat.
Thanks for the clarification. Thanks for that.
I have another question then.
Yeah, sure.
Yeah, I really I like the wooden approach for the mystery box room. This would be away from the more technical side. Do you feel that's something that could be viable for outreach? I mean, I'm assuming the plan would be for it to be laser cut, and you can laser cut quite a lot of plywood at once. So is that something that you think could be used for outreach as well, getting it into schools as a quick, easy way to make a frame?
Yes, I think I completely agree to what you said, that was the key idea, But as you're aware, due to the COVID restrictions, we could not have access to our labs and our workshops within our university. So that is something that could not have been done. But had we had the access to these equipments, I think that would be the most accurate way of making these cut extrusions, these windows, making these slits for heat dissipation. That is the key laser cutting idea.
Okay, thank you very much, judges, for those questions. Just one more question from the crowd and stuff, and then I think we're probably out of time. But so what skills, kind of soft skills, do you think you developed most in this competition?
Sure, I think I can take that as well. As you're aware that any competition, including this itself, gives you an opportunity to learn a lot of new skills, to develop your current ones. And as you're aware, we've been working on this mission for over 9 months now. And for sure, we have gained, number one, a lot of knowledge about the satellite platform and how to design one. We've learned to work in a team, to be able to adapt to the changes that have been brought due to the COVID, where we have had to work completely online, and we have had to adapt ourselves for that. So that's definitely what we've also learned. We've learned to be able to meet our assignments on time, punctually. So time management is also a soft skill that we have acquired. More importantly, for this particular mission, we've had the chance to explore our creativity and give attention to critical thinking to solve a lot of the problems. As you're aware, it's not easy to build a complex system like the one that we have in place at the moment. How these systems are integrated, how they go in together requires a lot of critical thinking, and we've been able to practice that aspect within this competition.
If I can say something, for all of us, this was our first time. So we started from not knowing how transceivers work to afterwards in the end understanding how everything is integrated together. So we divided up really well our work within each other, and therefore, since everyone had sort of a different system to connect together, I think in the end we understand very well how a cube satellite is manufactured, and we look forward to having an opportunity to build it, because that's when it actually feels like we have put our practice into place. Yeah.
Thank you. No, thank you very much. That's a very comprehensive answer. We've had another question in the chat about end of life, but I think we've covered that with the other previous question anyway. So thank you very much, Leicester team. That was a great presentation. It's been great to see all your work throughout the year. Thank you very much for joining us. We'll probably rejoin the live stream again about 20 past, where we'll have the call from the presentation, from Airbus, so from Robert, who's the systems engineer on Envision. So thank you very much, Leicester, and we'll go to an intermission now and then rejoin at 20 past. Thank you.
Thanks very much, guys.
Perfect.
Hi, hello, sorry. Welcome back to the Satellite Design Competition Day. We currently have Bob with us, who will be presenting an Envision talk from Airbus. So it's going to be really interesting. So Bob's a systems engineer, as I'm sure he'll tell you about more in a second.
Indeed.
So I'll hand over now. So thank you very much.
Thank you. Hello, everyone. My name is Bob Hopton. I am a system engineer for Airbus. I've been working here for the last 10 years, last 3 of which have been in system engineering. And more specifically for this talk, for the last 2 years, I've been working on the Envision Phase A study, which has now been successful and has been selected for the Phase B study, which will then lead towards the implementation bid in 2023. So my main goal for this talk is just to go over some of the interesting mission parameters of the Envision mission, and then go into some of the more challenging requirements, and then talk about a couple of the design decisions we've made to meet those requirements, as I think that's best of this competition. So starting off very quickly with the mission parameters. So at the top level, Envision is the M5 mission for ESA's Cosmic Vision program, looking at activity on Venus. It is going to hopefully answer important questions about Venus, namely, is it still geologically active? How has the geology evolved through time? How is the atmosphere linked to the geology? And how the Venus interior works. To that end, we have a suite of instruments, which include the VENSAR, which is a reflector SAR provided by JPL, which will be measuring the surface morphology. We have the VENSPEC, which are 3 spectrometers provided by a consortium of European universities under DLR, the German Space Agency, studying the composition of the atmosphere and the surface. And finally, there is the SRS, which is a subsurface radar studying the crust of Venus down to about 1 kilometer with a 10-meter resolution. There's a nice image on the side which shows basically where the different instruments are looking through a cross-section of Venus. And then finally, there is a passive experiment, the radio science experiment, which will be using the communication subsystem of the satellite, using the radio occultation in the communication to Earth to measure the gravity field of Venus as we travel round Venus. So those are the instruments. Now onto Venus itself. Venus, of course, is the most similar planet in the solar system to Earth based on mass and diameter. It has a few differences to Earth, namely, it has no moon. It rotates incredibly slowly at just over a quick jogging pace at the moment. And also it spins retrograde, which we're not exactly sure in comparison to all the other planets in the solar system. Which, as a consequence, means that Venus is almost a perfect sphere in comparison to Earth and other planets. It is not an oblate spheroid like Earth is, which means that on Venus there is no J2 perturbation in the orbital mechanics when orbiting Venus. So there's no J2 function to move the right ascending ascension node of an orbit to enable a sun-synchronous orbit, which would be the one that's more typically used for a Earth orbiting mission. In this case, of course, Venus orbiting mission, which means we have effectively a drifting polar orbit, which complicates some functions. Especially this complicates the science because it means that due to the low rotation and the fact that we can't have a sun-synchronous orbit, the science becomes quite difficult to do repeat passes. So whereas usually on Earth we would see one area we're interested in every day, on Venus we'd see it every year effectively. Venus year, that is. So although we have a 4 Earth year, 6 Venus year mission, we will only be able to observe the regions of interest a maximum of 6 times, which means that scientists are currently being very careful to make sure we don't miss any of those important periods. Thirdly, just by the way the planets work, the Earth-Venus distances varies quite a lot, from a minimum of 0.3 AU to 1.7 AU, which complicates the data architecture dramatically, since the bandwidth available at 1.7 AU is a fraction of a percentage of what we can get at 0.3 AU, which means that we can't really do the more detailed SAR observations at the furthest distances, and instead we either have to find a way to store the data, find a way to maximize the comms link at those times, or we just have to do all those data experiments when we're closer to the Earth. Finally, in addition to being close to the Sun than the Earth, Venus is also the hottest planet in the solar system, which complicates the thermal design of the mission. There are a few other peculiarities of Venus. It, for example, doesn't have a magnetic core, a magnetic field, so we don't have to really worry about radiation around Venus, apart from just standard background radiation. But that's not really a sizing case for the mission design. So yeah, I'm just going to show you a nice picture here of the regions of interest on the Venus surface. As you might be able to interpret from the image, generally the major regions of interest are in the mountainous and volcanic areas, or where we suspect volcanoes are. Generally, the scientists aren't too worried about the plains between the volcanoes, but having been to some of the science conferences, I know there are some Venus scientists who would bite my ear off for saying that, because they are interested in some of the changes over time. So we will hopefully, over the course of this 6 Venus year mission, look at these regions of interest and see how they change over those periods. And then, just for a bit of extra interest, some of these areas are actually the areas where the Russians landed back in the 70s with their quite impressive, basically tank-based landers, which survived for only a couple of minutes in the intense Venus heat and corrosive atmosphere. But they took pictures of the Venus surface, which we hope to match up with the SAR images as we observe the planet. So that's the mission setup and the difficulties around Venus. Oh yeah, sorry, a bit more about the coverage and observation requirements. So, as I say, there are different coverage profiles defined by ESA at the moment. ESA being, of course, our customer for the UK. We have various different instruments on at different parts of the day. You can see that we basically have a 15 orbits period to look at. That is approximately a 24-hour period, so that's what we will work with. And we have, as you can see, quite a large comms window in the middle of it, which is the maroon section, which is what is required to transmit all the data required. Because, just as a bit of context, it is very unusual to take SARs outside of Earth orbit, because they are one of the most data-heavy instruments you can put into space. Then generally just have various times for rotating. Of course, the various instruments have different pointing requirements. The major pointing requirement being that we need to have one face of a spacecraft as a nadir deck, which points towards Venus for as much as possible during the science period, which is mainly for the VenSpecs. And then the VenSAR has a similar requirement, but also needs to point the satellite by about 40-50 degrees to enable it to have an eastward or westward scan of the planetary surface. Now, for anybody who has been paying attention, there is a American mission, Veritas, which has got some very similar instruments and goals coming up, which will be launching around about the same time as Envision currently. And we are planning that these two together will hopefully increase the overall knowledge of Venus. So, in case anybody asks about that one later. So yes, in total there are 8 different science operational profiles which have been defined across the different distances, but I won't go into too much detail there, although there will be a graph later on where I'll point them out again. And this actually is the basic science operations at the maximum distance. So, moving on then to the sizing requirements. So, Taking then the mission parameters, we then need to look at some of the other sizing requirements which come out of the mission parameters, and also just general requirements that the customer, in this case ESA, have put on us. So the various payloads I mentioned at the beginning, they mass to 200 kilos, and we have a nominal launch mass currently of 2,700 kilos for a variety of given launch dates. Of course, this changes depending on what we choose to do exactly with the launcher, but I'll mention that again in a second. For the power, we of course have to provide power for all the instruments, whilst unable to rely on, apologies, my picture has covered up the word there, but I should be rely on the full solar illumination, because as I said, we will be in a drifting polar orbit, which means that at any one time the satellite effectively has a fixed array with relation to the solar illumination, whereas normally on an Earth observation mission you would have the solar arrays tracking the sun as you go round the orbit in the midday, midnight. And then of course we also have, at the other end of the spectrum, we have a dawn dusk orbit at some points as well, where we effectively will see the sun throughout the entirety of the orbit, where the power requirement is not too much of a concern. So our sizing case becomes this midnight orbit where the solar arrays are effectively fixed in comparison to the solar illumination. I've already mentioned communication. We need to provide useful data at the maximum of 1.7 AU to Earth. So as you might be able to see from the image, we have quite a large antenna set up, considering the size of a spacecraft. The antenna currently is 2.5 meters in diameter, which compares to the overall spacecraft length of 2.8 meters, which is currently defined by the focal length between the SAR reflector and the SAR feed, which SAR reflector up here, SAR feed over here. Then you got the SRS boom down here, which is the subsurface radar I mentioned, and then these 3 sets of holes are the spectrometers on what is the nadir deck, which, although this picture is not very good for it, this nadir deck will be pointing at Venus throughout most of the mission to allow the observations. Now, the final constraint we have to worry about is the thermal. As I mentioned, Venus is exceptionally hot and we are very close to the sun. In addition, due to how the orbit works out, we need to define one phase of a spacecraft, which we can define as the cold phase, which is achieved through flipping the spacecraft at various points during the mission. But yes, we need a cold phase for the SAR electronics, because the SAR itself requires a power of 1600 watts, which, as you can imagine, puts out quite a lot of thermal power. So we have to have large amounts of radiators on this face to dissipate that heat. And then the spectrometers themselves need to be kept at quite cool temperatures to allow them to function. So you can just see poking out behind the feed, we have a sort of radiator system here to allow a thermally isolated radiator to be, well, yes, the radiator thermally isolated from the rest of the spacecraft to allow the vent spec in this corner to keep its nominal operation temperature of minus 60 degrees Celsius, approximately. So yeah, those are the main sizing requirements. So I'm going to go into 2 of them really here, just to give an explanation of the trade-offs we made to get to a mission design. So the most important one at the moment for us is the mass and mission analysis. So there are 4 stages to the transfer to Venus. For some reason some of the wording has not come out well. Oh well. So 1, there's supposed to be an Earth here, but yeah. So we have number 1 here, which is the launch. Number 2, which is the interplanetary phase. Number 3, which is the Venus orbit insertion. And then number 4, which is the final science orbit acquisition. So for launch, we have 2 options: direct insertion into interplanetary transit versus a insertion into high Earth orbit. Here, we basically have to decide whether we want to have a higher V infinity when leaving the launcher, so that the launcher can't take as much mass, but that does mean we get to go straight into Venus without having to worry about high Earth orbit. Or we go into high Earth orbit where the spacecraft carries more propellant to allow a delta V burn to escape from Earth orbit, which gives a bit more flexibility in when we leave, and gives a better. It's a bit better things like the calibration of the spacecraft after launch. Essentially, we're still properly choosing because the launcher we're planning on using, the Ariane 6-2, is still in development, so keeps on releasing new figures. Our most recent baseline was direct insertion, but we have now received some recent high Earth orbit figures, which makes that look to be a bit more likely for delivering more mass at Venus. But of course, what we have to consider then is for a high Earth orbit, we have to worry about more radiation at Earth due to going through the Van Allen belts a few times. It's not a lot, but it's just a consideration. And also, more importantly, we have to worry about larger tanks to carry more propellant to leave Earth, and then also do the Venus orbit insertion and the acquiring Venus site orbit. So it's currently a trade-off between how much mass we deliver to Venus compared to how big we want to make the spacecraft, how big we want to have the tanks to carry the propellant to Venus. Then secondly, the interstellar transfer is not actually much of a trade-off. It's just a matter of working out the most efficient route for a given launch date. So I have below 2 examples. So we have a long transfer where basically we take 444 days to do a full orbit of the sun, and then bring ourselves slowly to Venus. Or we have the much more direct 135-day transfer, which is only really possible given given the locations where Earth and Venus are at any time. And just to give a bit of context, we can only really repeat the exact same transfers every 8 or 9 years, I believe is the figure. So we are currently looking at a wide range of launch dates to see when are the best set of launch dates to give us the mass at Venus, but also have good backups in case there are delays to the spacecraft, which require us to use a year later. So currently we're looking at a 2031, 2032, 2033 launch, but we'll see how that develops over the course of the Phase B. Then the delta V required for Venus orbit insertion is just basically defined by the infinity of when we get to Venus. It's just very much a simple calculation of how much propellant we need to slow down into Venus orbit. And then we have the most interesting part, which is the lowering ourselves down to Venus orbit. So we start off at around about, oh gosh, I can't remember actually now, a very high orbit around Venus when we initially get there, and we need to lower it down to a semicircular orbit of 550 to 250 kilometers, which is more circular but slightly elliptical. So we looked at several options of that, which I will look on the next page. Yes, so we looked at several options to maximize this transfer. There are, of course, looking at the propulsion methods, either chemical propulsion, electric propulsion, or a hybrid of chemical and electric propulsion. And then there is also the option of using an aerobraking system in the Venus atmosphere to reduce the apocenter of the aerobraking orbit, which is very much a trade-off between using aerobraking or using delta V to achieve a science orbit. And then it's all a matter of finding the most efficient method of achieving that orbit versus minimizing the delta V needed to achieve the final orbit. So with an electric propulsion, it becomes quite easy. We would just spiral down gradually to Venus and then spiral down gradually into Venus science orbit. It is technically the most mass efficient way we found. However, in order to achieve electric propulsion, we would need solar arrays about 4 times the size versus chemical propulsion, which has further complications when we have to worry about the maneuverability of the spacecraft in Venus orbit. So, of course, with larger solar arrays, we have a larger moment of inertia when rotating, so greater use of the reaction wheels, which in turn requires greater greater propellant usage to offset the wheel offloading, which becomes more complicated. Also, unfortunately, and what it came down to is electric propulsion is still quite expensive for the deep space missions. It's great for the small, what's being used for the geostationary satellites for the next generation of telecoms, but unfortunately for deep space, it's still proving quite expensive. Hopefully that'll come down in the future, which will make it more easier, because the other options we found all included using aerobraking, which adds in its own complications, not least the fact that we have to worry about additional thermal loading of the spacecraft from interaction with the Venus atmosphere. And in addition to that, worrying about things like atomic oxygen, degrading the structure of the spacecraft, degrading the solar array performances, which are fun things we have to worry about. In addition, because we can't guarantee that the spacecraft will not tumble, we have to worry about protecting the instruments from at least one aerobraking orbit where they will see the full front of the aerothermal flux, which could be damaging to them. So aerobraking is, of course, the most efficient way to get to reduce the delta V requirement, but at the same time, it adds in a whole host of additional problems, and it costs a certain amount because the ESA ground stations will need to have constant tracking of the aerobraking path to make sure nothing is going wrong. So, to cut a long story short, currently we are looking at a design which uses chemical propulsion with aerobraking, although we are trying to minimize the aerobraking as much as possible by working out if we can find more efficient ways of getting to Venus to allow us to have more delta V available in the Venus orbit, which would allow us to lower the aerobraking initial orbit and reduce the overall amount of time aerobraking. Just since I didn't mention, the hybrid was also too expensive for similar reasons to the electric propulsion, because it also has a similar electric propulsion system to the electric propulsion option. Then just to say what the aerobraking looks like, to just describe the aerobraking, we would have an initial large elliptical orbit around Venus. We would start to decrease the pericenter, which brings it inside the Venus orbit, inside the Venus atmosphere. And then through successive passes through the atmosphere, a braking effect occurs on the spacecraft, which gradually reduces the apocenter until we finally get towards around about 1,000 kilometers for the apocenter, at which point we walk out of the aerobraking corridor and then just circularize the orbit into the final science option. Yeah. Just an additional worry about Venus, of course, is also we have to worry about the major conjunction between Earth, Sun, Venus, where we won't be able to communicate with anything orbiting Venus for about a 30-day period, which means that we also have to worry about the possibility of popping out of the aerobraking corridor during the middle of operations to avoid the possibility of anything going wrong with aerobraking whilst we're unable to communicate with the satellite, which again adds additional delta V, which we have to take into account for. So if we have a lower initial aerobraking duration, then we can look at fitting it in between conjunctions, which is another goal that we're trying to achieve. So yeah, then I just go on to another design solution, the power. So there are several points during the mission where there are potential sizing cases look at for power. Again, during aerobraking, when we get very close to the end of aerobraking, around here, the entire duration of an aerobraking orbit is about an hour, hour and a half. Which means that with the 10 minutes we have to worry about for aerobraking and 20 minutes of rotating the spacecraft to get ready for aerobraking, and the possibility of 40 minutes of eclipse, we only have around about 40 minutes of illumination. So we need to make sure that for the limited power needs of the aerobraking and potential safe modes, that we can recharge the battery to a safe state in each aerobraking period. The other one is at the beginning of aerobraking, there's a possibility of a long eclipse, whereby although the initial orbit could be around about 12 or between 12 and 24 hours around Venus, there will be approximately 2 to 4 hours of eclipse behind Venus during that 12-hour, 24-hour elliptical orbit, which is significantly longer than any other point during the mission, which also potentially drives the battery sizing for making sure the spacecraft survives throughout the eclipse. Then there's just general throughout most missions. When you go to build one, you have to start worrying about safe modes. We need to make sure that even in your worst case mode, you have to have sufficient power to survive the safe mode, which in our case is basically just trying to reacquire the sun, at which point we'll have illumination on the solar arrays to keep ourselves powered. So our safe mode is currently not too long, but we'll see how requirements change when we get to the next phase with the ESA mission. And then there's also the Venus orbit insertion. Due to simple stresses and simple appendage flexibility on the solar arrays and on the SRS, we are currently looking at a situation where we will have to have the solar arrays depointed from the sun, such that any flexibility in the long flexible SRS boom can't interact with the solar array, which means we have a period around Venus orbit insertion where we have to we might not have enough, we won't have solar arrays, so we need to make sure that for the 20 minutes of Venus orbit insertion we have enough power available from the batteries. However, despite me saying all that, the actual sizing case is the comms window at maximum distance. As I mentioned before, we have around about 6 hours of comms period with which to communicate with Earth. Now, admittedly, we might not have all of this as actual active comms, as depending on the orbit around Venus at the time we want to communicate with Earth, we could be in eclipse with respect to Earth for half a day, so we only have to worry about half of it. But for the purposes of sizing it, we need to assume that there's comms power on for all of this maroon period, which requires additional power. In addition, we have to worry, of course, about the instrument modes, but they're not too bad. So yeah, and then just as I was mentioning earlier about the different levels of comms over the course of the mission, you can see with these spikes are where we are close to Earth, so we're able to provide more data to Earth, and then we drop down to the long distances away from Earth, and then during major conjunctions there is no data generated, so we have no data to transfer. So hard to see, but it peaks at around about 320. It's 320 gigabits per day generated. But due to how much we store in the mass memory, when we're close to Earth, we will look to download around about 500 megabits per day. Sorry, not megabits, gigabits. Yeah. So that's one of the solutions we found to the problem of the distances, is to store the data to then transfer later. So yeah, just going back to the power then. You can see here, this is the blue line in this graph is the power load. Again, I'm not sure why the graph picture has failed to show it properly here, but blue is the load, red is the solar illumination flux. So these these curved lines, these are the instrument modes where we have the spacecraft pointing the DIA, so the solar array is effectively flat. And then during the comms modes, because we need to keep the spacecraft stable for the RSC experiment, we actually have them constantly pointed at the sun. So we have a much more flat curve, which means there's more power available during the comms, but at the same time, you can see that there is a higher nominal power required during those modes. And then you might also see these blue spikes here. These are the then SAR modes. As I say, they are 1600 watts of power required for the SAR, which is a dramatic transient case on the system. So it's a couple of minutes for these. So they're not a dramatic load on the system, but they do need to be taken into account for certain things like the well, basically the charging of the battery needs to be able to sustain it and needs to be able to survive the sudden instantaneous VENSAR activity. But that is a design, that is not a design sizing case. That's just something you have to worry about when it comes to high powered missions. But as I said, we have a sun synchronous. We don't have a sun synchronous orbit, so we have the fixed arrays during the midday orbit, which is our worst case. And yes, so from all this, we now know the energy requirement of the satellite over the course of an average day during worst case. And then we also know how much flux there is. So from that, we can size the solar array and battery accordingly. It comes out to about 10 meters squared of solar array once you're taking into account additional radiators to keep it cool and general packing factors. And the small amount of we have to worry about for shadowing, which and then the battery is around about 40-50 kilos to take into account all the long eclipses and power being used during these eclipses. Actually, that's one final point. You also see that the actual worst case is when the comms needs to take place during the night, at which point there's a higher load during the eclipse, which has an increase on the increased need for the battery sizing. So those were just two and a half if you count power and comms together of the design problems we have to solve for Envision during the phase A, and the sort of things we had to go through to work out the best solution, and then a brief description of what the solution was, which led us to this spacecraft design, which is our PR shot of the spacecraft. But yes, is there any questions?
Thank you.
I'm sorry, I think I overran a bit there.
No, that's okay. It's really interesting. So we're very happy for that. No, it was a really good talk. We've had a couple of questions come in.
Sure.
Yeah, so I think we have about 5 minutes for questions, and then we can get back to the normal stuff at 6 o'clock, the other teams. Yep. So that's fine. So the first question is, did you ever consider sending multiple assets to achieve an interferometric arrangement with SAR payloads and achieve topographic data on Venus? Sorry, that's quite a long one.
There was at one point a discussion about if we wanted to send multiple spacecraft, but the problem is we only have enough money really in the ESA pot for one mission to Venus, and we couldn't then have enough mass on that launcher to have more than one satellite, just as how it came out. Unfortunately, a lot of the good ideas in the space world kind of hits the wall of there's just not enough money for them and just not enough launchers. But yes, it was considered at one point.
Okay, that's really interesting.
Yeah.
So
actually, on that point, since Veritas is going at the same time and doing similar things, we will be able to hopefully compare results, which should give more data points for the interferometry. Yeah.
Okay. Yeah. No, that's good. If anyone else wants to submit questions as well, then feel free to use the Q&A at the bottom of the page. So another question was, what are the main engineering or otherwise challenges experienced with or anticipated for this mission?
So really, the major issues we're concerned about are pretty much what I said. It's error braking, making sure the spacecraft can survive the aerothermal flux passing through the Venus atmosphere, the general thermal environment of the planetary albedo and also the solar flux, whilst having instruments which have delicate thermal requirements and excessive power requirements which require greater radiation. And then finally, the communications again. It's just the sheer amount of data we need to transfer for the SAR to Earth from the maximum distance is one of the more challenging things we found during the phase A.
That's interesting. And then I think we have time for another question. So why are we looking at necessarily the SAR for the topography? Is there another way we can measure the topography?
I'm afraid I kind of left the science world before really getting into that sort of thing, so I don't know off the top of my head if there's a better way of doing the topography. All I can say is that this was the one selected by the mission scientists, and we've ended up this way.
Okay. No, that's good. That's a perfect answer. It's very reasonable. No, it's a very interesting mission.
I think
thank
so,
you
yes.
very much. Yeah,
Cool.
sorry we haven't had more time for more questions.
Yeah.
But if we get any more, we'll send them along to you, and then we'll let you answer them, because we're going to have to go on a break now. But yeah, thank you very much, Bob. Thank you for giving us your time.
Okay.
That was a really interesting talk.
Yeah. Thank you, everyone, and good luck with the rest of the day.
Oh, thank you. Okay, welcome back, everyone. Thank you for sticking with us for this call. We just had a shortened version of the 15-minute break that we would have had there. So now we're back with the University of Strathclyde presentation for their Strath Squared satellite. So I'll let you guys take it away.
So we're from the Strathclyde Aerospace Innovation Society, and Strath Squared is our entry into the UK SED satellite design competition. So a wee bit about our team from Kieran.
Hi everyone. So as Rory mentioned, we are the Strathclyde Aerospace Innovation Society, and at the society and the university, we are responsible for developing the Universities of Strathclyde's first ever CubeSat development, StrathCube, and which is to encourage the sustainable usage of space. So the purpose of us entering this UK SEDS competition is for senior Strath A students developing this CubeSat to try and pass down the lessons we've learned about space mission design to younger generations of students who are undergraduates, to try and get them to have the skills they need to pursue space mission design.
Okay, thank you. Thanks, Ian. Right, so we're going to start with the critical design review. So just a recap, CubeSats are a class of nanosatellite and have already been proven to be effective for Earth applications. So now organizations like NASA are considering them for interplanetary applications as well. So our mission was to design a 3U CubeSat that can detect and analyze several different data sources from a simulated lunar environment, otherwise known as the mystery room. The team first split into subsystems, creating their own derived requirements, and then a trade-off analysis of commercial off-the-shelf components was then performed to optimize the system's performance and keeping to a £500 budget. Unfortunately, though, due to COVID, the team was not able to build and test our system.
So from our trade-off analysis, the final system was costed as £460 with a 10% system level margin. More than half of that cost was attributed to the payloads. And again, using a 10% system margin, the final mass of the system was 2.3 kilograms, which was well under the specified limit of 6 kilograms. The battery from the power system and the flywheel from the attitude and orbit control system were by far the most heavy of those components.
Okay, so when in the mystery room, the payload must be able to detect objects of interest, temperature data, light data, and electromagnetic signals in the range of 915 to 921 megahertz. So objects of interest was left open-ended, so the team decided to collect both visual and proximity data. Starting with 6 different payload configurations, the trade-off analysis performed settled on the following components: a camera and LiDAR to detect objects of interest, a thermal camera for temperature data, a spectroscopy and a lux sensor for both wavelength and intensity light data, and a radio module with a monopole antenna to detect the EM signals. As we were expecting the data sources to be placed at different heights in the room, the field of view of the system had to be increased. This was achieved by mounting payloads on a rotating plate as shown here. The plate angle is controlled by a pulley system with a servo motor mounted at the opposite side, which provides accurate control. The advantage of this belt pulley system is that it allows lots of space for the plate to rotate freely. Apart from the camera, which interfaces directly with the onboard computer, the payload subsystem is controlled by an Arduino Nano board. It oversees motor actuation as well as data acquisition and processing.
The power system of our satellite consists of 2 voltage buses, 3.3 and 5 volts, supplying the payloads and all supporting subsystems. The battery has a capacity of 6,500 mAh and can provide 11.1 volts, which was deemed appropriate for a system having a drop-off voltage of 6.72 volts. Additionally, a variety of protection circuitry components such as buck converters, latch relays and fuses, among others, are integrated in the design to ensure that the satellite is protected against over and under voltage, reverse connection and over temperature. In addition to those, the operation of components is constantly monitored and the power can be shut off using a software kill switch or an external mechanical kill switch, adhering to all SDC regulations.
On the right, you can see a high-level data architecture for the data handling subsystem. For the central onboard computer, the team chose to use a Raspberry Pi Model 4B for its high computing power and integrated Wi-Fi functionality. However, both the type and number of interfaces to other subsystems was a concern, and so 2 Arduino Nano daughter boards were included to handle the AOCS and payload subsystems. These daughter boards communicate data back to the Pi, which decides the current active payload, the AOCS position, and plate angle for a fully autonomous system. For the communication subsystem, the team decided to use Wi-Fi. This was the simplest option and needed no extra components, as the Pi already has Wi-Fi functionality. The Pi uploads the processed data to a server, which is then accessed via a laptop in mission control.
The AOCS has a function to determine where the CubeSat is relative to the main light source and rotates to a new desired angle. The final design consists of the listed components. The motor has an encoder which negates the need for a controller, and this benefited the power requirements and has a large torque with a lower RPM. The maneuvers are pre-calculated in small angles of rotation to achieve the desired angle. Both a magnetometer and a gyroscope were chosen to increase the accuracy of the IMU, with both components connected to a low-pass filter so that noise disturbances were removed from the data. The LDR array has 2 LDRs on each face of the CubeSat to account for redundancy, and the flowchart shows how the data will be transferred through the LCS via the actuator, then the MIU and light sensor, and back to Arduino Nano. Lastly, a Simulink model was created to simulate subsystem level tests.
Okay, so a model of the satellite was created in SolidWorks and is shown here. So only Z-axis control for the AOCS system reduced the constraint of where it was placed, unlike in an actual CubeSat. And so we decided to put it in the top 1U of the satellite, with the power and data handling components placed in the center to be closer to the payloads.
So the Mystery Room mission would be comprised of 3 phases, the first of which was startup and calibration, followed by orientation, and then finally refinement. During the first of these, connections made with mission control, and all sensors are calibrated. Phase 2 consists of 3 7-minute sweeps surveying the room. Each sweep has different active payloads, with the plate angle constantly oscillating between plus and minus 45 degrees. The refinement phase returns the points of interest recorded in phase 2 to analyze them and decode any messages.
Okay, so yeah, again, unfortunately, due to COVID, we weren't able to get lab access to build and test it, but we did participate in the extended design review. So for this part of the competition, the aim was to identify, analyze, and relay images of historic lunar landmarks. This was obviously a large pivot from the work completed previously, as it was focused less on low-level design and more on actual space systems engineering. Again, subsystem-derived requirements were created, and a trade-off analysis was performed. Once the design was finalized, a decision on the feasibility of the mission was to be made.
So the orbit of the CubeSat was designed to achieve 4 main requirements specified. I had to visit all of the landmarks specified. I had to maximize the dwell times over the sites. I had to be capable of taking high-resolution images. And finally, I had to degrade in more than 3 months. So this required a trade-off and a compromise between the orbital elements. Ultimately, it was found that when using an eccentricity of 0.2, 70 degrees inclination, and a semi-major axis of 2,237 kilometers, this yielded the best or the most optimum results, as you can see from the ground track passing over the ground stations and the table of dwell times. So although the requirements specified that the RelaySat had to have an altitude of 100 kilometers, its inclination, rate ascension, and argument of the pericenter could all be varied. So therefore, a trade-off again was undertaken to maximize the time in view of the CubeSat. And it was found that the only orbital element that made an impact was by changing the inclination, which changed the communications window. And it was found that simply matching the inclination of the RelaySat with the CubeSat was the most effective in terms of communication time. So once, moving on to the launcher and launch date selection, once in the low Earth orbit, around 4 kilometers per second of delta V is required to transfer the payload to the moon. And based on the transfer vehicle on the RL-10 engine, the total mass required to be launched was 798 kilograms. We selected the Falcon 9 rocket to achieve this, as it can easily handle this payload and has a relatively low cost, especially when using ride shares, which is very typical for CubeSat missions. The launch date was designed to minimize the period of longest eclipse to impact the power system as least possible. And as the mission was going to be more than 3 months, long launch dates 3 months apart were considered. So ultimately, a launch date of the 15th of September 2021 was chosen, which is actually only about 3 weeks away. And the feasibility of station keeping was also investigated, but ultimately discarded from the design. And this was due to the fact that a chemical engine was far too heavy and an electrical engine could not provide the necessary thrust to be worthwhile. So therefore, the end-of-life strategy for the CubeSat is to allow it to crash into the moon, avoiding cluttering lunar space. This will occur naturally due to the orbit selected and occurs 162.5 days after the CubeSat first enters lunar orbit. And crucially, the impact site will avoid hitting any current or past lunar surface missions, which makes this site a safe option. And you can see that on your screen just now.
Okay, so for the payload selection, we looked at payloads aboard existing lunar orbiters like the Lunar Reconnaissance Orbiter. And we considered several different types of payloads, including optical cameras, thermal cameras, and spectrometers. While selecting the payload, quality of data from the payload, mass, and power were considered. And we quantified quality of data as the ground resolution, which is the smallest distance that can be represented by 1 pixel on an image, and also how useful the data would be to the mission. So we eventually decided on the GomSpace NanoCam C1U camera module with a 70mm lens, and this was due to it had the best ground resolution compared to its mass and power specs. Its image sensor has a bit depth of 10 and a 4:3 aspect ratio to result in a file size of 3.75 megabytes per image. So as the satellite passes over one of the specified landmarks, a series of pictures will be taken and stitched together to form one continuous photo. So taking images from such a height brings the curvature of the moon into play. And what that does is it actually distorts the edges of the images. And so what the stitching does is if there's an overlap between them, we can actually edit this distortion out. So the time taken between these photos to ensure an overlap can be calculated and depends mainly on the altitude of the satellite. So this will be recalculated by the CubeSat for every pass to ensure the optimum data acquisition over every landmark. The raw data will be stored as well as a JPEG version of the image and the initial processing performed on board. The JPEG and processed data were assumed to be 20% of the image file size. With an average of 2,700 seconds of payload communication time per orbit, it was found that only 9 full payload packets could be transmitted. It was instead decided that the compressed image and processed data would be sent as they were the most important, with the raw images being transmitted during the end-of-life descent.
The ALCS will have 5 modes throughout the mission. The tumbling mode is used to stabilise the CubeSat after deployment, pointing mode when the payload is collecting data from the lunar surface. The recharging mode will be in play when the solar panels face the sun to charge. Communications mode is used to communicate with the relay satellite in the lunar orbit. And lastly, safe mode will be used if there's any troubleshooting on board. The ALCS must counteract the disturbance torques experienced throughout the mission, and in worst case scenario, a 0.032 millinewton-meter torque is needed to rotate through an angle. For the EDR, we selected the ADCS 100 module. It can perform the manoeuvres that the CubeSat will undergo throughout the mission, such as deployment and detumbling. It will also meet the design criteria listed. It consists of 1 tactical gyroscope, 6 sun sensors, and a 3-axis spherical motor. It also has an integrated processor which relieves pressure from the main onboard processor. The parameters are tabulated and the limits are within the values calculated for each manoeuvre.
The power subsystem is comprised of primary solar arrays, a 2,364 milliamp hour battery, some backup solar arrays, and a power control and distribution unit. And on the right here, you can see how the solar arrays will be deployed. So we first defined 3 operational modes for the power system, each with their own power budgets. Daylight mode for when charging, eclipse mode for when the battery is needed, and a safe mode for an emergencies where only comms, data handling, and power subsystems are switched on. The worst case daylight and eclipse scenarios, as shown, were used to construct these budgets and size the relevant components. For the onboard data handling subsystem, the OBC-P3 module was selected, which actually comes with 2 separate OBCs contained within it. It was decided that one of them would act as a central command module, while the other one would handle payload and AOCS systems. If one were to fail, the other would switch to become the central command unit, and payload processing would be halted. So on the right here, you can see the avionics architecture of the satellite with all the relevant interfaces. So this module has 128 gigabytes of storage, which is more than enough to store the data acquired during the mission, and we can store over 20,000 images. For the communication subsystem, we chose to use our own values for the CubeSat, but kept the antenna and ground station values given by UK CEDS for the RelaySat. We decided to increase the data rate to 128 kilobits per second for both telemetry and payload data, while staying in the S-band. So then we chose an S-band transceiver and patch antenna, and this transceiver uses GMSK modulation and a bit error rate of 10 to the -5, resulting in a required 11 decibel EB/NO value for a valid downlink signal. The average communications window per orbit for the CubeSat and the RelaySat was 2,971 seconds, in which telemetry data would be transmitted first to ensure nominal operation before downlinking the processed payload data.
The base values as shown in the link budget were taken from the transceiver and antenna datasheets. The RelaySat was assumed to have an antenna noise temperature of 150 Kelvin. The path distance between the RelaySat and CubeSat was taken as the worst case scenario. Due to this consideration, greater certainty in the margin is ensured. Both margins successfully exceeded our baseline margin of 3 decibels.
Thermal control is essential for any satellite. In order to determine which control methods are necessary, a thermal analysis must be carried out. In ideal circumstances, this would be done using software that can accurately model heat transfer throughout the structure. However, such tools were unavailable to us. Therefore, a more basic thermal analysis was carried out with the goal of determining the hot and cold cases for the satellite during its orbit. A hot case of 21.8 degrees and a cold case of -14.3 degrees were calculated, necessitating thermal control in the form of patch heaters. These allowed targeted heating of components that would fall below their minimum operating temperature without heating other components. A coating of vapor deposit aluminium will be applied to the satellite body, which will act as a form of passive thermal control. The low absorptivity and emissivity of this material are essential in allowing the CubeSat to remain cool during its hot case. The satellite structure needs to fill certain requirements, like reserving certain sites for components like the solar arrays, or a whole U for subsystems like the AOCS or payload. The chassis is made out of aluminium 7075, which provides ample strength and weighs less than 400 grams. This is less than 20% of the entire CubeSat mass. As previously mentioned, there are 2 configurations available for the satellite, one with the backup arrays stored and one with them deployed, as seen in the picture above. The sensor mass does not vary significantly from one case to the other and is always about 12, 0 and -1 millimeters on the X, Y and Z axes respectively from the geometric center of the satellite, which falls within ESA regulations of a 10 centimeter margin. Various checks were performed, such as ensuring that all components fit inside the structure, checking component masses, and confirming that the moments of inertia can be managed and counterbalanced by the AOCS.
So the EDR mission itself is set to cost around £350,000, including the satellite itself, plus launch and operations costs, with the satellite costing around £120,000. The final mass with a 10% margin ended up being 2.3 kilograms, which is again well below the 6 kilogram CubeSat maximum.
Okay, so for the concept of operations for the EDR CubeSat mission, first of all, we have the flight plan here, whereby the Falcon 9 launches from the Kennedy Space Center and enters LEO. Following that, the separation occurs and a translunar injection is performed. And finally, we intersect the sphere of influence, enter final orbit, and begin operations. So you now can see our nominal operations here, where the CubeSat will upload pictures to the RelaySat when in range, and it will take pictures the lunar landmarks as it rotates. So you can see that this first enters the desired orbit, detumbles, begins operations, and then at the end we have the end of life procedures. And you can just see a summary of these points on your screen.
Okay, so just a bit of discussion to close this off. We believe we've submitted a really strong design. We think our mission analysis and payload design, especially for the EDR, was really strong. If we had to pick a weak point, it would probably be the thermal analysis, as we didn't have access to the software that we wanted to, so it's quite basic. Commenting on the feasibility of the mission, we believe this mission would benefit from being a 6U or a 12U bus instead of a 3U. That would allow you to have a propulsion system on board, allowing you to pass closer to the surface and have station keeping, which allows you to take higher resolution images of the surface, as well as just fitting larger and better payloads onto your system. So overall, the team found this project challenging yet really rewarding for us undergraduates. There was a steep learning curve for more early year students, especially with the space systems engineering aspects, and some of them hadn't taken on a project like the CDR before. But we think it achieved our goal at Strathace of getting them good experience for CubeSat design. So thank you for listening. We'll be taking the questions now.
Thank you very much. That was a really strong presentation. It's great to see all of your work and everything that you've managed to do. So thank you very much. I don't know which one of the two judges wants to ask questions first.
If you want me to stop sharing, by the way, I don't
know. It's up to you. You can keep it up if you want.
I'll start with a question then.
Yeah.
So what did you actually use to do your thermal analysis?
We used the SMAD document. Very basically, essentially, we considered the satellite as one big radiator, and we took into account the incident solar energy and the solar energy due to the albedo effect from the moon, plus infrared emission from the moon. Did a very basic thermal equilibrium calculation to arrive at our hot and cold cases, depending on whether it flips or not.
Cool. Yeah, it was good to see. Did you do, if you were going further and if you were using software, is there anything else you'd consider in thermals?
Geometry plays a huge role in how much heat it would absorb. Also, another thing that I would have liked to have taken into account is the time in the sun. Obviously, that's going to affect how much energy the structure absorbs, and then it's going to be the same for in your eclipse case as well. But the biggest thing is obviously you're going to have one section where your components are you're going to need them cooler than another section, but you're going to have heat is going to leak throughout the satellite. And that's something that I think would have been interesting to have used software to try and model, but we weren't able to do that.
Yeah, I think I think the approach you took was really good, and I think with software, what you want to look at then was actual how is the heat in the satellite transferred. But yeah, it was very good to see that. I think Phil, have you got a question?
Yeah. First off, well done, Strathclyde. It's really good. Enjoyed that. And my question is on the taking the images. You mentioned that you'd process and stitch them together. Was that done on the satellite? On your
that wasn't something that I considered when writing it. I just knew that we were going to stitch them together, but we did leave space for the second OBC module to perform some primary processing on board, so that would probably be involved in that.
Because I'm just thinking if you had any considerations as to why you would why would you prefer to do that on the satellite, or just send the images back and stitch them together on the ground? Obviously, you talked about compression, which you do on the satellite before you send, but I just wondered if you had any thoughts or whether you'd maybe stitch them on the ground instead.
Well, again, I think the compression is a good point, because as we've seen from the communications window, we weren't actually able to send a lot of the raw images down. So I think it was more a kind of a data problem and more of than a sort of decision on where we were going to stitch them together. So I can't say I considered that during the...
Okay. I think
just to add on Rory's point there, I think the data handling module that was actually selected is quite a high power module anyway. It's the Space Inventor OBC P3, which I think probably would be capable of doing the data processing. Obviously, we didn't work out kind of a timeline of that and really go into the depth, but we did select quite a high, a very capable processor that we assume would be able to do that.
The camera module itself actually performs, it's got an onboard processor and it performs the compression before passing it over to the OBC. So then I was assuming the onboard processing would more be identifying landmarks and identifying any interesting features that you spotted in the pictures. But
and another one that I've remembered was you mentioned kind of what I would call like a semi-stable orbit. So you planned it would be up there long enough to fit your requirements, but it would crash eventually. I think you quoted 160 days or something like that. But then you mentioned a kind of an impact site. I was wondering how well you could justify that impact site. Could you really trust your kind of calculations that far in advance to see exactly where you'd impact, given the kind of perturbations from the moon?
I think it just really depends on having a high fidelity enough propagator to allow that. So the tool that we built was custom built from scratch. So it's a full numerically integrated propagator tool. So the main thing that we wanted to take into account, obviously being around the moon, was the inhomogeneous effects of gravity. So we considered that up to quite a high degree, because that's it's unlike on Earth where things like J2 are really dominant. They go quite high up, so we made sure to include that in our calculations. It's a great point, like you say, that if we were to actually do the mission, we'd really want to ensure that pretty much every perturbation, like third body perturbations and so on, and solar radiation pressure, were all considered before we could finally be confident on that landing site, like you said. But because we're selecting a fairly specific launch window, I think it would just depend on, at the preliminary stage of the design, I think it's good enough for now based on the level of fidelity we had for the propagation tool. But yeah, it would certainly be something we would build on just to be more confident in where we actually landed.
Yeah, if I could just follow on from that quickly, I think that's another reason why possibly a larger bus would be quite good for the mission, as you'd be able to, like some of the other teams have done, have an actual dedicated deorbit mechanism to be a lot more, instead of relying on a really accurate propagator, more just one burning straight into the moon. But again, there's no regulations on. There's not really any regulations on where you can and can't crash into the moon, but we didn't want to. We made sure that, or from our calculations, we weren't crashing into any past or future landing sites.
Your custom approach, out of curiosity, was it using MATLAB?
Yes,
I've been down that road before.
It was actually mostly Ian, who isn't here today, but we it was his first time doing any sort of orbital mechanics work at all, and we basically I think that's one of the really good things about what this team have done. So Rory and I are a bit older. We work on kind of the actual CubeSat we're trying to develop at the university, and we kind of just gave the tools to these guys, and they went off and built something like that when they're still in relatively early phases of their studies, which is for me one of the things that I've enjoyed most about this project, is just seeing them be able to kind of take it as their own and really run with it, and potentially even do stuff that we can't do, and we're several years above them. So yeah, it's been cool to see.
Great, that's good to hear about the team. Nice, thanks.
Okay, well, thank you, judges. Do you have any more questions? Oh, okay, I think you've kind of answered the questions we had from the chat. We had, what did you find the most enjoyable about the project? But I think you just kind of said that. So maybe from one of the younger students, what did they find most enjoyable about the project?
I would say it's really interesting to learn from older more experienced students rather than lecturers. I mean, obviously everything, certainly in my view, everything I've been taught so far didn't really have any relation to space flight at all. So to be able to learn entirely new skills that weren't on the curriculum has been fascinating, and to have to take brand new information and then solve a problem with it straight away has been a real experience.
Oh, that's very interesting. Thank you. That's great. Great to hear that it's so enjoyable. So thank you very much, Strathclyde. I think that's all the questions we have for you at the moment, all the time we have. But thank you very much for your presentation. It was very nice to hear from you.
Cheers. Thanks a lot.
Thank you.
Thank you.
Thank you.
Thank you very much, guys.
Thanks.
Bye.
Okay, welcome back to the UKSAID's SSPI Satellite Design Competition day. So here we're back with CRANSAID's satellite team and a vicinity mission. So CRANSAIDs are the only team to enter on the TRR side of the competition, which we discussed at the beginning, meaning that they have managed to build their CubeSat. So there'll be a slightly different presentation to the other teams that we've seen earlier. But we're all looking forward to it a great deal. And we'll hear a little bit more about their actual prototype later on as well. But for now, I'll hand over to CRANSAIDs.
Okay, thank you very much. Hello, everyone. Thanks for attending this presentation. First of all, our team would like to thank UKSAIDs and the SDC team for organizing this competition. Our team is inside the CRANSAIDs Association at Cranfield University that is involved in several space-related competitions and research projects. So this is the content of the presentation. We will introduce the vicinity team, and then we'll explain the competition. We will continue with the design and building of our satellite, Vicinity, going through the different work packages. And then we will conclude with the testing and the results of the final challenge day. During the presentation, you will see this icon of Q&A. That means that we can discuss more about what is being presented during the questions and answer session at the end. This is our team. We are all master students at Cranfield University, and we all have different roles within the team that you can see here at the top, and we are divided into these different work packages. So the main driving objective behind this competition is to judge the effectiveness a nanosatellite payload can achieve in order to acquire as much scientific data from historic lunar landmarks as possible. So in order to do that, a theoretical mission has been conducted to evaluate the mission planning, and an analog lunar mission has been done to evaluate the potential hardware. For the analog mission, the project focuses on the design, build, and operation of a 3U CubeSat that we've named Vicinity to identify and analyze the different sources of data signatures of the mystery room, which we will explain later. And for the theoretical mission is about the design of a high-level theoretical lunar nanosatellite mission, stating which is the orbit that the satellite should be injected into to maximize the revisit times of historic lunar sites and landmarks. But apart from the competition objectives, our team has gone beyond its requirements by considering also design benefits on the CubeSat industry and space sustainability. First, because our CubeSat is modular. You can see here some movable plates and these 3D printed parts that make it reconfigurable. This allows the CubeSat to be adapted to any payload and to be reusable, so being more sustainable. It's also of easy access for things like calibration, component replacement, component upgrades. And finally, the team has developed a payload configuration tool that is very helpful to visualize how the sensor's configuration change. So to understand within the team the integration of all the work packages. This is the project schedule. It's divided into 3 different phases. First, a preliminary design review, then the critical design review, and finally the build and test phase. And I will now hand over to my colleague, Gemma.
As mentioned, the theoretical mission is mainly related to the mission planning. The objective was to select a 2-year lifespan orbit that maximized the revisit time of the given historical lunar landmarks. The first 3 months would be used for active data collection and the spare 21 months for passive data collection. The first step to select the orbit was to plot the location of the lunar landmarks that were given in order to have an idea of the orbital elements that could be used, especially the inclination. Then, a lot of research had to be done in order to understand the kind of orbits that could be used. Most low lunar orbits are unstable, mainly due to the irregular distribution in the mass on the moon. Thus, for the satellite to be able to stay in orbit without eventually crashing, there were 2 main options. The first one was to constantly monitor and compensate for the effect of the perturbations in orbit. However, looking into sustainability, this option was far from being optimal. Therefore, the one that was chosen was to use the so-called frozen orbits. Now, this is a group of stable orbits that basically are able to mostly cancel all the perturbations. Within this set of stable orbits, the team performed different analyses in order to select which was the optimum one with a commercial software called SDK. Now, once the orbit that we considered to be the best option was defined and fixed, the simulation was repeated with 2 cameras with a 5-degree field of view in order to make it much more realistic. This, of course, reduced the total revisit time count when compared to the simply passing above, but we considered that it was much better. As for the end-of-life strategy, a lunar impact was chosen. According to regulations, the region selected for the impact shall not have any historical nor relevant geographical importance. Thus, both poles in the hidden side of the moon are feasible options. And now Jack will present the analog lunar mission.
Thanks, Jan. So now for the analog lunar mission. This is what was actually done here on Earth and is how we evaluated potential hardware. So the analog lunar mission is about hanging our satellite from the ceiling in the middle of our room. It will spin on one axis and it will detect different sources. There's a main light source which simulates the sun, as well as objects of interest, a thermal source, light sources of different wavelengths and intensities, and a radio source which will send an encoded message. This relates to the theoretical mission by being a platform to test our sensors, and this was our structure and configuration. We stuck to the 3U dimensions as specified by the competition. We adopted modular structures where possible so that we could adapt to our different payload designs as they changed over the period. And we also used laser cut and 3D parts where possible. In the end, we came in far under mass budget with just under 1 kilogram out of the 6 kilograms possible. And now for Echo.
Now for the payload, the question we asked ourselves was obviously how to choose the sensors, but more precisely how to quantify the performance of many valuable options. So first, as said previously, we did a custom simulator, which was a great internal communication tool. It was also used in our trade-off study to rule out the actuation of sensors. We then moved on and did a simulation on SolidWorks. This was great, but did not give us any valuable data. So we ended up doing a simulation on MATLAB, as you can see on the lower images. Next. Here are our sensors for the initial payload design. So for measuring the distance and the taking pictures, we chose one stereo camera and one ultrasonic sensor, as we can see just under it. Then we also had 2 thermal cameras, one on the side and one at the bottom. 3 light sensors acting as a custom sun sensor, and 1 radio module. For our actual payload design, we ditched the ultrasonic sensor because of lack of time and space, and one of the thermal camera was not available, so we ended up just using one on the side. As you may have seen, we don't have an instrument to detect the wavelength because the only affordable spectroscopy sensor there is on the market, so the triad spectroscopy sensor that you see on the screen, only works within a few centimeters, and our requirements needed 1 to 5 meters distances. So obviously that's not working. And for a more commercial spectroscopy sensor, we were talking above a cost above 170 pounds. So the cost and risk were too high for us to include that payload instrument. However, we still have a rough estimate of the wavelength values with the light sensors.
Well, now I will explain about the electrical subsystems. First, to design Vicinity's power subsystem, we must first define the CubeSat's power requirements. The most power-demanding components are the Raspberry Pi and the reaction wheel motor, while all the sensors on board can be powered internally by the Raspberry board. The expected energy consumption of these components is 6.2 watts-hour for the 30 minutes duration of the test. The main power subsystems components are a LiPo battery, the kill switch to cut off power, which is a competition requirement, the electronic speed control unit for powering the reaction wheel motor, and the battery elimination circuit, which transforms the battery voltage for powering the Raspberry board. Finally, on the bottom diagram are presented the voltage paths across vicinity. Next, please. Thank you. Regarding the OVDH and communication subsystems, a Raspberry Pi of 4 GB of RAM is chosen as the onboard computer since it complies with the requirements of CPU, amount of RAM needed, and it supports the generated data rate. It is also compatible with the rest of the equipment, and the number of pins available is enough to accommodate all of them. The communication between ground control and the satellite is established by means of an SSH SFTP connection, allowing to remotely execute the preloaded scripts on the satellite.
So now for the control. Although the system defined by the competition looks quite simple, we opted for a closed loop control so that any unaccounted for perturbations in our rotation could be reduced. We also opted to use a reaction wheel, as that is the industry standard, so it's a good analog. We decided to keep our costs low for the control system, using a cheap ESC and a brushed DC motor, as well as a 3D reaction wheel to actually be our mouse. This was our perfect plan at the start, but as with everything, no plan survives contact with the enemy. And in our case, the enemy was definitely our hardware selection. So during testing, we faced many challenges. The development of the control strategy was tough, and mainly because of our ESC. It had a non-linear response that showed some sharp steps in the speed response of the satellite. And also throughout our testing campaign, we discovered that the friction environment was degrading. You can see this by the different lines. The blue line was a test we did at the start, and the green line was a test we did at the end. And the system saturates almost at half the input value. So in the end, we came up with an innovative solution to solve this. It allowed us to exploit our hardware shortcomings. So we ended up using just a P controller that rode one of the large steps. Since angular momentum was not conserved in our system, it meant we could step around our rotational axis instead of maintaining a low constant speed. We had to change our derived requirement to a data acquisition metric instead of a speed metric, but it let us complete our mission.
As you see, our initial cost estimations were about £800. The whole project, including the building of our mystery room, ended up costing us slightly above £650. So we're very proud of having made it under budget. This money is coming from our Cranfield Student Association, RS Components, and the grant from UK SEDS. Now for the testing phase, this portion of the presentation has been shortened due to time constraints, so we can either talk about it in the Q&A or in our second presentation later. Here are the 3 typical tests we did on our 4 sensors. As you see, they all pass their tests. Next. So some important test results, not all of them. First, the stereo camera test proved that the accuracy was really good. The object was at 2 meters and was also detected at 2 meters. Then for the light sensors, our calibration allowed us to reduce the error within the plus or minus 5 degrees optimal margin. And then the thermal camera range test allowed us to see an object at the far end of our lab or mystery room. And now for the challenge day, so bear with us a moment, you will see our realistic and way more stressing mystery room in a few slides. Next. So here are the typical and theoretical sensors we should have included in our mystery room, but we did some small changes to that, starting with the LEDs. As said before, we don't detect the infrared, so we used a blue, red, and green LEDs in our room. We replaced the hot plate with an iron, and instead of using a directional antenna, we used an omnidirectional antenna from SparkFun. So in theory, that's the beautiful mystery room we should have had, but in practice, our lab looks more like this. In the ideal scenario, we were not expecting a very stressing situation. However, our mystery room in our lab turned out to be pretty noisy. This allowed us to add some realism to our testing campaign. It caused a harder detection of object with the stereo camera, and the light from the LEDs was bouncing everywhere. Nonetheless, as you will see, the mission was still a success. And to quote our mentor's colleague, Theresa Williams from Astroscale, click, "The moon will not be clean, and neither is our lab." Next.
So this is the operations plan for the challenge day. It's divided into 3 different phases. For the initialization, in the commissioning, the different subsystems are activated and confirmation data is sent to ground. Then for the validation, ground receives the initialization data from the subsystems and validates that everything is working correctly. As you can see, the speed stabilization is done later. This is because for the acquisition of the electromagnetic signals, the library of the radio module was not compatible with the rest of the libraries. So we did the electromagnetic sources detection first, and then the CubeSat started rotating. The core is divided into, let's say, day and night. During the day, we have the sunlight. The sun is detected, and the stereo camera takes pictures. And then during the non-lit phase, or the night, the LEDs detection is done. You can see that the thermal sources detection is done in both phases. And finally, for the data processing, we allocated some time while the test is being run to the validation of the received data. This validation time allows us to assess quality of the data, then turn around and gather more if needed. And then we process the sun location data, the stereo camera data, that takes a bit longer because of the images, and then we process the other sensors data.
Here you have a summary table of our results. As you can see, all the sources in the mystery room were detected. We also detected almost all azimuth and elevation angles within the optimal 5 degrees margin. That yellow box you can see with a slightly higher error is caused by our hardware limitation, as Jack mentioned earlier. But with a longer data acquisition period or a better motor, this would have gone to green, obviously. As previously said, the IR LED was not included, and the position of the radio signals could not be measured since we're using an omnidirectional antenna. However, as bonus information, we captured a picture of each source and measured their depth from the satellite. Here we have a few results. I won't be going through too much detail on those, but we can see we have some missing data or some gaps in our data, but despite that missing data, we still have met the requirements. We also found out we had a IMU drift, but again, this was due to our poor choice of motor. So with a better motor, this would entirely solve the problem. And finally, for the thermal camera, the picture above is the thermal camera when not looking at the iron. And obviously, the bottom one is when looking at the iron, we can clearly distinguish the shape of the iron. And on the right side, we have the radio messages received. So that's it.
So for the stereo camera, we've put here only the images of the objects of interest, but we took images of all the sources. You can see here the first object that was at 2.3 meters from the CubeSat center. And here you can see the depth map of the object where it's calculated to be at 2.2 meters. So it's quite good in accuracy. And the second object was placed at 1.2 meters from the satellite, and its depth was calculated at 1.3 meters. That is, again, quite good. We can say that even the environment is more noisy than the one the competition would have provided. The results are quite good. And anyway, the moon won't be clean. So to conclude, we've made a list of possible improvements for the next vicinity generation and some tips to work in the team that we can cover in the Q&A session. And as conclusions, all the different sources in our mystery room were identified. The competition's requirements are met with 3 concerns that we have already explained. The infrared sources are not used, temperature range is not proved, and the wavelength is approximated. Vicinity sensors cover a significant surface of the mystery room, thanks to the rotation of the homemade reaction wheel. Positions in azimuth, elevation, and depth are collected within reasonably good error margins. And we give more information than required by the competition, as we give the depth and images of all the sources. Also, we have to highlight Vicinity's modularity, making possible the reusability of the CubeSat for other payloads, reducing non-recurring costs and making it more sustainable. Apart from that, the team has designed a simulation tool for the configuration of the payload that helps the visualization of its interaction with the rest of the subsystems, and has made a list of possible improvements for the next generation Vicinity. Overall, the team has performed really well. We have very positive comments from two senior engineers at Astroscale, our mentor, Mark Moktoyuk and Sandor Nemeti. And that's all. Thank you very much for attending the presentation. And if you have any questions, we are glad to answer.
Thank you very much, Cranfield. That was a really good presentation, and it's really exciting to see that you've managed to build and set up your own mystery room so well. I know this is something that we were kind of a bit worried about, whether people could do it, but you've absolutely smashed it. So that's great to see, and it's great to see you got such good data as well with everything. So well done, and thank you very much. I'm looking forward to seeing more about your prototype a bit later on as well after the break. So do we have any questions from our judges? I think Phil is unmuted.
Yeah, great to see such a big team. And I guess that came with its own challenges as well. So my first question was going to be, how did you go about organizing yourselves at the start to make sure you could utilize everyone as well as you could?
Yeah, so at the beginning, so you mean how we decided to build?
Mm-hmm. Yeah, how you decided to structure the team, I guess, and how did you decide who got what job?
Okay, so we have this slide. So we decided to divide it into different work packages that I put in the beginning of the presentation. We can go there afterwards if you want. And each of the work package has a team lead, so that so communication is brought on all the team. We had a presentation meeting each week with all the team, and then each work package had a meeting also. And we divided it depending on the structure of the satellite. So if I go back here. So this is the team leaders for each of the work packages, and we had systems, payload, mechanical, power and communications, onboard data handling, and mission for the theoretical mission and the ADCS.
Thanks.
I guess I have a similar question, because I was going to ask the same thing.
Sorry.
Following on from that, how did you actually then manage during the project so many people and all the subsystems and making sure all that information was well communicated?
Yeah, so we used Teams and WhatsApp to communicate, and we have a weekly meeting always. It was always online because we couldn't make it face to face, but we ensured that. So, for example, the simulator that Irina did with the CubeSat to see how what the sensors were looking to the mystery room was very good for communicate between payload, ADCS, and structures. So we tried to do these kind of things so that everyone could see what the other were working on and what they mean when explaining things. And even if it was online, it was quite easy to do it like this. And then, through Teams, we had the different channels. It's quite organized, and we did a Gantt chart so that everyone knew their tasks, but also the other tasks, to understand the integration of everything and why one has to do this task, not because it integrates with the other tasks of the other people.
Okay, thank you.
I could also add to that regarding the lab access and COVID, and also people having internships. So we lost some people from on campus, and we also were limited in the number of people being able to access the lab. So we had to choose those people who would participate more technically, others more from home. We also have a schedule for the lab access because we're sharing it with other teams from CanSets. So yeah, we spoke a lot with our lab technician to have access.
Yeah, it was quite difficult to achieve the lab access at the beginning, but well, we did.
Can I also ask about, so it sounds like you had a lot of trouble with this stepper motor, and you came up with some great ways of trying to overcome this. I guess if you could do it again, what would you do differently to try and avoid that? Or do you think you just got unlucky with a bad batch, I guess?
So I think I can try and give an answer on that one. So in terms of the actual faults in the hardware, I think we spent a total of £10 on our motor, and I think £8 on our ESC. So we spent almost the smallest amount per work package. So if everything worked as specified on the packages, we'd have been fine. What actually happened was that the inside the gearing of the motor, it was a standard brush motor that went into a little gearbox, and inside that gearbox were plastic gears. So what we suspect happened is that they degraded. If you could hear the noise that it made, you'd know what we were meaning. And the ESC trying to maintain the speed of this motor caused a lot of issues. So yeah, you could hear the teeth of the gears hitting back and forth as there was a lot of room between them, which caused issues. And then also the ESC itself had the large spikes, as you can see from this graph of kind of the input not changing very much, and then suddenly a massive change in the response of the satellite, and then the control system not knowing what to do and dropping back to the lowest value. So this is actually the test where it should have been a normal control loop, but what we found is that this method actually made us oscillate close to our operational speed. And the reason that the control was such an issue is because we had a requirement from a thermal camera to have a very low rotational speed of 1.6 degrees a second. So if you can believe me or not, this is in radians, but there's a red and a green line on that, which was our deadbands, and this is our true satellite speed. So you can see how far from an optimal situation this was, even with a proper control loop and no fancy different method. Yeah.
Thanks for that. Thanks.
No worries.
I just wanted to add one little thing. If we had to do it again, I think we would choose more a brushless motor used for the camera gimbals, for example, because those motors are really torquish and they are able to rotate really slowly. So they are perfect for such a direct drive use. This brushless motor from camera gimbals. This would be our choice now.
You also might not have seen the same degradation as well, I guess, with the brushless one as well. But yeah. Thanks.
Okay, thank you, judges. Is that all the questions you have? Or yeah, okay. We just have a couple of other questions. So, what was the biggest kind of new learning area that you saw in the competition? I guess it would probably be in your build. What was the thing you had to learn the most about for this?
For the competition, I think Edward can talk about the sensor, the spectroscopic sensor.
Yes. With sensors, we learned a lot, but yeah, first, as everyone, we chose the spectroscopy sensor from SparkFun. I was a bit skeptical about how to use it, and there were no data everywhere on the range it was operating at. So we decided to just buy it and test it. So that's one way to learn how one sensor works. Again, all that technical work has paid a lot, I think. We don't come from very technical background for most of us, so having a hands-on experience is really great. Yeah, I mean, then it's all personal experiences, but I haven't been playing with Raspberry Pi before. Or
I think something that we found was integration hell as well, where we could get everything to work perfectly on its own, and then we went to put everything together. For example, the radio receiver, it worked perfectly. We put it together, 2 libraries don't cooperate, everything crashes and nothing works anymore. And having to find ways around using different libraries or recoding parts of libraries to get things to cooperate was a big learning curve.
Oh, that's very interesting. Yeah, those are interesting problems you might not think about when you're first going into it. Okay, I think we have time for one more question, and that was, what's the hardest part of setting up the mystery room that you found in the end? Other than trying to get access and get time in the mystery room, the actual setting up process. What do you think?
I think I can comment on one thing, which is the actual hook interface. So we modified ours from the actual specification, because what we found is that even with a good bearing, but obviously things degraded over time in our setting, but with a bearing, we still had give in the rope that would cause like a buildup of angular momentum, and then it would release. So trying to control with that at a very low speed was almost impossible. So at the end, we ended up having a 3 connection points of ropes going to a carabiner that then hooked onto our bearing. So it meant that there was no rotation in that, which is something that for future competition bits, that might be a good idea to set up to isolate, so it's only rotating around where the hook interface is.
Yeah, for this stereo camera also, as you can see, this mystery room is, well, not a mess, but it has many, many things. So the stereo camera was detecting everything. So to detect the objects of interest, the stereo camera didn't know what the object of interest is, because everything was of interest for the camera. So yeah, that was a bit complicated.
Maybe one last thing for the light sources. As we can see, the red one in the back of the room, it was really bright, so we saw it really clearly. But the blue one on the floor was the complete opposite, so it was really hard to see it. So maybe have a threshold of light intensity for the light sources would be great to help every satellite to detect it.
That's very interesting. They're very interesting kind of problems that you've had that, yeah, I haven't really thought about. But no, that's good. Definitely the roof anchor as well is something good to take note of, I think. Yeah, well, thank you very much. Thank you for presenting. We'll be back with you again very, very shortly, but I think on the stream we'll probably go to a break and then we'll come back in kind of a few minutes and then we'll talk a bit more about your actual prototype itself. And then directly after that, we'll have another talk by Airbus, which will be great. And then straight on to the award ceremony. So thank you very much for this presentation and talking about your whole project. Yeah.
Thank you.
Thanks, guys.
Okay, well, welcome back again. Sorry, we're slightly behind schedule, but this is now the presentation from Cransets on their build and test of their prototype satellite. So this is different to their actual presentation. But yeah, so I'll hand over to Cransets and let them show you what they've made.
Thank you, David. So hello everyone again. I hope you enjoyed the last presentation. Our team is going to present now the build and test phase of Vicinity, and we have a video for that. So enjoy. So that's been our build and test. About the requirements, we want to emphasize that during this test phase, we have proved we meet 49 requirements. 3 are met with concerns that I will explain later. And we are indeed way under the mass budget requirement. The requirement is of 6 kilograms and our budget is of 1.7 kilograms. We are also under our cost budget. So these are the requirements we have as concern. For the first one, we lack of equipment to test the temperature range, but we designed the CubeSat considering these temperatures. A part of the light sensor requirement is not met because no affordable sensor was found to detect light in the infrared range. And finally, the source's location is met for all sources except for the antenna, again, because of cost budget. So an omnidirectional antenna was chosen.
Hello, I'm Paul. I'm the mechanical designer of this satellite project. And the first part of the mechanical design is the structure, so the wall frame of the satellite. So you can see on this picture, on this slide, a render, a picture of the real satellite, and a little animation. You can start the animation. For this structure, we had three main design requirements. So the first design requirement was from the competition itself, so to have a 3U dimensions. Our choice was to have a modular structure because from the beginning we didn't know all the components which would be inside. So we needed a structure that could adapt itself to all the components that we will choose later in the project. And the final main requirement was, of course, to use the tool that we had available in the laboratory. So for example, a laser cutter or 3D printer. You can see on the main, on the middle picture, the horizontal mounting plates with an altitude modularity, the vertical mounting plates, which has an altitude and a depth modularity, a battery quick release system, the hook interface with the bearing housing. I designed a structure which is stiff enough to prevent any bending because of the weight of the component. And you can see that we have an easy access to all the components. It's easy to assembly. We use 4 aluminum L rails for guiding the CubeSat while launching it. And we used finally high quality hardware like chamfer torque screw and lock nuts. Next slide, please. So the second part of the mechanical design is the mechanisms themselves. So that means all the movement and actuation inside the satellite. The choice of the team was to use no sensor movement. So we have only one movement, which is the whole satellite rotation around its vertical axis. And the choice was to use a reaction wheel design. You can see on the electrical diagram that we use a 12-volt lithium polymer battery powering an ESC, and this ESC is controlling the reaction wheel motor, which is a reduced brushed motor. This motor will power the 3D printed main wheel on which we can screw adjustable stacked aluminum disc to adjust the inertia of the reaction wheel. And on the electrical diagram, you can see that we deleted the servo motors because we don't have any actuation for the sensors. Thank you. Next slide.
Okay, sorry about the animation, Paul, but it was the animation you saw in the video. So these are the sensors we have in the satellite, and we are going to talk about the testing of each of them. So starting with the stereo camera. First, we do the calibration. As you can see, the camera detects in both images the chessboard edges, and then the rectification is done, where the lines that you see are put straight, so we minimize the errors of the depth map. With that, we solve the correspondence problem that is about locating the 2D points in both images. And with that, we construct the disparity map. That is the difference in pixels of the points in the two images. So knowing these points, we can do with basic triangularization some calculations to know where this 3D point is. And we obtain the depth. This was the test that was done for the stereo camera. We put an object 2 meters away from the CubeSat. And as there's nothing else but only the object of interest, it's quite easy to know where the object is in the depth map. And the error, as you can see, is null. However, in the mystery room, as you have already seen in the previous presentation, it was really noisy. It is more difficult to detect where the object of interest is. But anyway, we were quite successful and the errors were quite low.
Now for the thermal camera and the radio module, it was quite simple. After validating the output temperature of the thermal camera, we tested the range of both equipment. Next. We detected a human almost 5 meters away from the thermal camera, and we've had signal transmission between the two radio modules that we see on the right at a distance of 1.5 meters. Next. Now let me guide you through the functioning of our custom sun sensor before talking about the testing. So first, I have to mention that the useful data of that sensor is when the satellite is directly facing the source. In other words, only when the azimuth angle is right, the elevation angle of the light source can be computed. The example on the right shows a blue light bulb with the line of sight of the 3 light sensors, where the top light sensor sees it almost directly. Next. So here is the typical response we would get when the satellite is rotating. So 3 similar curves with different peaks happening when the satellite is facing the source. And from there, we basically compare the 3 peaks together. We obtain 3 possible elevation angles, and we take the average of those. Next. So as I said before, the light sensors are useful when directly facing the light source. As we see on the left, here the range of possible elevation angles goes from the floor to the ceiling, as indicated by the orange arrow. So for testing purposes, we pivoted the satellite 90 degrees, so the possible elevation angles could be all at the same height. We then strapped a light bulb to a metallic support, as we can see on the top right, and moved it along that new orange arrow from left to right. Next. And from this test, the raw data were slightly off, but by applying a calibration function, we reduced the error within the optimal 5 degrees margin, as we can see here. Next. And here we have the real results from the mystery room, showing some light intensity values on the left. And with these, we can compute the plot of elevation angles as we see on the right. Again, the real elevation angle from this graph is only the peak value. And finally, we also did a range test for the light sensors for a distance from 1 to 5 meters. The signal was always positive, so we can detect the light source from anywhere in the room. And finally, here is a list of possible improvements for the second version of Vicinity. I won't go into much detail about it because of time constraints, but I will be more than happy to discuss in the Q&A session. Thank you for listening, and enjoy the rest of your evening.
Thank you very much. That was a really interesting presentation again, and thanks for talking us through your CubeSat. It's really good that you've managed to build it. Just see if there's some questions that have come through from the crowd. Yeah, so which part took the longest to build is a question.
To build as a structure or to build as the whole system?
I'm going to say, okay, which kind of work package took the longest to build from electrical and actually physically building it as well?
So I think we had 2 main areas of work going at the same time. So Paul was doing the structure, while a few of us were doing all about the sensors and payload. In the end, payload took a bit more time, obviously, because we need to integrate it in the structure and then do all the code behind it. So I would say the payload, but we should not reduce or diminish the time spent on the structure as well, because it holds everything together.
Yeah, and the reaction wheel, because of the problems we had.
I think on the actual assembly, there was one day where we spent about 7 hours in the lab just plugging in cables into the Pi and into our sensors and making all the cables not get in the way of the reaction wheel. That was the day, the final integration that took the longest out of everything.
Oh, well. Okay, that sounds like a long day. It's all work though in the end. It was all worth it. Okay, so what was the biggest benefit for you guys from the build phase, from actually building your prototype? What benefit do you think it had for you the most, as opposed to just doing the report?
Well, first, I would say that as this has been done during a pandemic, having to build the satellite made us gather together and work together. That was amazing after all that part online. But also we've learned a lot, I would say, of all the errors we had during the build and test, because of the libraries incompatibilities, some code errors. It's also that it's very important to integrate everything together and understand properly what the other has, the other needs, and how it's going to put it in your CubeSat for the structures part, but also for the software and all the hardware. So I would say, yeah, that.
I would add the satisfaction when everything worked in the end. That was a great benefit.
Absolutely.
Yes, it's really satisfying. It's a big satisfaction to build a satellite. It's keeping all the members of the project really motivated to make this project. And also when we design something on the computer and when we make a theoretical design, everything always works, and it's really hard to see our own mistake because we design our thing and we have only our own eye to see that. So building it allows us to see exactly what we do right, what we do wrong, and this is how we'll really learn to see all our mistakes and how to fix them, how to solve all the real issue, because the theoretical model is always perfect and everything always works on the theoretical model, but it's not the true life.
And that's why it's very important to allow some time for errors when you are planning your project.
Okay, and I think we have the time for the final question, which is just kind of from me. So that would be, if I was a student right now and I was thinking about doing the competition next year, what would you say about doing the competition? Did you be honest? You can say that it was horrible, but yeah.
Do it.
Yeah. Yeah, you learn a lot, not only, I mean, because all of us are students, we know what is having lessons and exams and everything, but doing this competition is completely different because you have to work within a team, you have to work with a budget, you have to look for sponsorship also, and when building, it's completely different of what you are studying in the university. So you learn how to work within a team, but also technical things. So I think it's, yeah, do it.
And the other part is that it's something to actually really make you stand out on your CV if this is the industry you want to go into. So during interviews, you'll get asked a lot more questions about this than you will about any actual university course project. So if this is what you want to do, it's really worth it.
I would also add, I would encourage everyone to build if possible, because in school or university, we often just do the first phases of a space project. Well, if you have the opportunity to build, then you go through all of the phases and until the end. So coming from nothing to having a real satellite in your hand, or a real prototype in our case, yeah, it's really a big satisfaction.
Oh, thank you very much. Thank you for your presentation and those answers. They're really great. Yeah, I think that's all we have time for at the moment, unfortunately, because we're behind schedule. But thank you, Cranston's team. It's been great to have you, and it's really great that you've managed to build.
Thank you very much.
Thank you, yes.
Thank you. Okay, hello everyone. Welcome back again to the Satellite Design Competition Day. Sorry that we're slightly off schedule again, but we're trying to get back on track. With us, we have Ian, who will be talking to us about the Solar Orbiter project and the mission. I hope that it's very interesting for you all, and you can learn a lot. Please feel free to ask any questions through the link at the bottom of the page anytime through the presentation, and then I'll ask them at the end. So yeah, thank you very much. And I'll hand over to you now.
Thank you very much. So my name is Ian Walters. I'm the Solar Orbiter Project Manager for Airbus. Unlike the presentation you had earlier on Envision, which was a phase A, we're now in phase E. So we're right at the other end of the mission. We launched it 18 months ago, but I'll show you a few pictures on that in a second. This is a 90-minute presentation I've compressed into 20, so I do apologize in advance. I'm going to go very quickly through it. Hopefully not too fast. I'll show you the most important points. So just quickly through the science objectives. I don't have many slides with lots of text on. Most of them are photos, but this is one of the few. Why do we need to get that close to the sun? We're going to go about 4 times closer to the sun than we are at the Earth, about 42 million kilometers, which is about 0.28 of an astronomical unit. It's a lot closer and therefore a lot hotter. It takes some risks to go there. Why do we need to get that close? So we're trying to really answer 3 main questions. One is, how does the sun create and then control the heliosphere? The heliosphere is a massive bubble of particles and fields which the sun pushes out way beyond the orbit of Pluto, right into the interstellar space. And the sun controls all of that, and we don't really know how it does that. It fills that space with the solar wind, and the solar wind doesn't originate below the surface of the sun. It actually originates in the sun's atmosphere called the corona. We don't really know how it does that, how it's created. And we also know the sun's activity changes every 11 years, and every 11 years the magnetic field flips upside down, and it's quite regular. I mean, why would it have such an irregular 11-year cycle? We don't really know why that is. So we have very limited models of how the sun really works, and this far away from the sun, it's quite difficult to really get a good handle on that. So we're going to go within the orbit of Mercury. We're going to take the closest ever pictures of the sun. We're in an orbit where, at the closest approach, we co-rotate with the sun. So the sun rotates every 25 days, more or less, and we kind of rotate with it. So we'll be following features on the sun as we go around, a little bit like geostationary satellites do on Earth. And then later in the mission, we're going to change the orbit inclination, which is quite unusual. We do that with Venus. I'll show you a little video later. And we can get up to about 32 degrees out of the solar system plane, the ecliptic plane. And that gives us then a view of the north and south poles of the sun. Now, they've never been seen. We can't see them from Earth. No other spacecraft that's gone away from Earth has had cameras to look at the poles of the sun. That's where the magnetic field originates. And we also know that there are holes in the sun's atmosphere called coronal holes there. Well, the models tell us there are. And we want to go and have a look. So we'll get the first images of the poles later in the mission. We have a complete laboratory of instruments. We have 4 in situ instruments. That means measuring local fields and so on around the spacecraft, and 6 remote sensing instruments. So they're looking at the sun or the sun's atmosphere. And the secret to Solar Orbiter really is to be able to correlate what we see on the sun and around the sun with what we actually measure locally to the spacecraft. Now, from Earth, that's quite difficult because the solar wind can take 4, 5, 6 days to get from the sun. So you're trying to correlate something you saw on the sun a week ago with what you're now seeing at Earth, and the correlation is really quite poor. By getting 4 times closer, that time gap will be a lot shorter, and we'll be able to understand, correlate much better what we see with what we get. And ultimately, this is trying to help us predict space weather. That starts to become more and more important, not only for us here on Earth, but also when we go to the moon and later Mars. We'll need to have a much better prediction for, if the sun decides to get really active and put out, say, coronal mass ejections, we need to know how fast they're going to go, in which direction they're going to go, how severe they're going to be when they get there. All of those models, we need to collect data. So Solar Orbiter is really the first scientific mission to go and do that. So if I can just start at the end. because we were fortunate to launch the spacecraft on an Atlas V launcher from Cape Canaveral, which was pad C41. For you history buffs, you might know that that's where the Voyager spacecraft were launched from in the 1970s. So quite a historic site to be at. Here you see the Atlas V booster erected on stand in December 2019, sorry, a year and a half ago. And then the fairing with the spacecraft sitting inside it is hoisted to the top of the rocket. Then the whole assembly of the launch vehicle is wheeled out of the huge building on the left. That's the Vehicle Integration Facility, or the VIF. And that's wheeled about 300, 400 meters to the actual launch tower. And then you can see on the right-hand side, the launch vehicle with a fairing sitting on top on the launch tower, completely dwarfed by 4 towers, which are lightning conductors. So you get a lot of lightning in Florida, and it's very important that we try to avoid that striking the launch vehicle. So they make sure that those conductors catch the lightning before it hits us. Then we had the launch itself. That was the 10th of February, Greenwich Mean Time. So actually 9th of February in Florida. It was 4 o'clock in the morning, Greenwich Mean Time, about 11 o'clock at night where we were. So that was a fabulous night launch. You can see a really beautiful trajectory by the light of the full moon as well. So it was really, really a perfect launch. So I'm just going to show, hopefully the video works. If it doesn't, we'll just move on, which shows the sequence of activities immediately after we eject from the launch vehicle. And I'll just talk to the video. So this is a configuration called the 411. It's got a single booster, which is very unusual. So it's an asymmetric launcher configuration. Fairing separation takes place 4 or 5 minutes after launch. When we get to a region above the atmosphere where the aerodynamic heating is low enough that the spacecraft can take it. Once we get down to the equator and we're launched into the correct trajectory towards Venus, which is the first port of call, separate from the fairing, then we initiate the LEOP auto sequence, which then automatically does about 12 sequences of commands. The first one of which is to get the solar rays out. You can see it comes in 2 stages. The first is what we call the jump out, where the solar rays come out under their own tension, and then we wind them out with cables in the second stage. Then the next thing we do is to deploy the 3 radio antennas. These are about 6-meter radio antennas. There are 3 of them. The first one we deploy on the top of the spacecraft. Then we deploy a 4.4-meter boom. That's always at the back of the spacecraft with some of the sensitive instruments on it. And then finally, the last 2 radio antennas. And we do that in a certain sequence because we want to keep those hinges warm. So we're constantly rotating the spacecraft to the sun to make sure that those hinges don't freeze. Then finally, we deploy the high gain antenna. That high gain antenna then allows us to lock on the high gain signal. First point of call then is Venus. As I mentioned, we flew past Venus just after Christmas last year, and we flew again on the second time about a week ago. You may have realized we did the second flyby over Venus this week. And then after the second flyby of Venus, we make one and only one return to Earth. So that's coming next. That's on the 27th of February this year. 27th of November, beg your pardon. So keep an eye out for that. You may be able to see it with the telescope. Then when we get into the operational orbit, you can see there are doors on the outside of the heat shield to allow light to enter the telescope apertures and take pictures. Of course, that also allows a huge amount of heat to enter. I'll talk about that in a second. So this is solar orbit in its operational orbit. Closest point, as I mentioned earlier, 0.28 astronomical units. So that's quite a neat video that ESA put together for us. And then here's another neat video of the sequence. You can see Mercury, Venus, and Earth there. After the injection, we do one Venus flyby, then a second Venus flyby, then an Earth flyby. And then after the Earth flyby, we drop down really close to the sun. We've been about 0.55 AU so far. So that's already quite close, quite warm, but we'll go much, much closer after this Earth flyby. Then there's a sequence of Venus flybys, about 5 altogether. Those flybys are designed not to fling us towards the sun, but actually to fling us out of the solar system ecliptic plane. So to tilt the orbit more and more and more. And eventually, as I said earlier, we get to 33 degrees inclination. So very quickly, just to look at what the spacecraft looks like. classical box with solar array wings, 18-meter span. We've got a high gain antenna, which is also quite classical for a deep space mission, 2.2 meter. We can get, when we're close to the Earth, 27 gigabits per day. Doesn't sound like a lot, but it's much, much higher than we can get with the S-band or the medium gain antennas. We've also got a heat shield at the front. So this is really the strategy for how we survive. Oops, we've jumped ahead, I don't know why. How we survive the intense heat. Basically, the heat shield takes all of the heating and we hide behind that. So the front of the heat shield is about 600 degrees centigrade. Behind that, it's more typically below 100 degrees centigrade. So quite a normal space environment. Right at the back of the spacecraft or in the shadow, we can get down to minus 180. So we've got instruments on the boom which have to be designed and qualified for very deep cold, even when you're close to the sun, which is quite strange because there's no atmosphere, of course. Even when you're very close to the sun, if you're in shadow, it's extremely cold. And then we've got the 3 radio antennas that you saw being deployed earlier. So the only things that get really hot, the heat shield, the high gain antenna is sticking out as well, and the solar array. So those are the 3 technologies that we've had to design and qualify for very high temperatures. Everything else is quite normal. But you'll see in a second, because the mission requires we always stay behind the heat shield, it means that the software has to be quite complex. So we've taken a complete laboratory with us. Each has different driving requirements on the spacecraft. I'm going to talk about that in a second. I won't go through them all in detail. I'd love to, but I think time won't allow. We've got 4 in situ instruments, so particle detectors, magnetic field sensors, radio wave sensors, and the solar wind analyzer, which is counting electrons, protons, and ions. And then we've got a remote sensing suite. So we've got an ultraviolet imager. You'll see a photo of that at the end of the presentation. We've got an ultraviolet coronagraph, so a coronagraph where they blot out the light of the sun, and you're then looking only at the atmosphere of the sun. A heliospheric imager. Sorry, that comes later. The polarimeter and helioseismic imager. So that's effectively looking at the magnetic field of the sun. It takes photos of the sun, but effectively in a magnetic field. So you can measure, if you like, which of the sunspots are north and which of them are south in terms of magnetic field. Then we've got the heliospheric imager that looks sideways from the spacecraft. So the purpose of that is to see if we would have a coronal mass ejection, so a big bubble of plasma flung off the sun, it would then track it as it moves across space from the sun to the Earth. We've got SPICE, which is a spectrometer, and then we've got an X-ray sensor as well. So this is a huge laboratory. Each of those instruments has got probably 3 or 4 sensors. So in total, we've got about 33 bits of equipment spread out all over the spacecraft, as you can see. And as I mentioned earlier, the boom is where we want to put sensors which would like to be as far away from the spacecraft as possible. Ideally, it's infinity, but 4.4 meters was enough. So we've got the electron sensor right at the tip so that electrons don't get deflected by the charge of the spacecraft. And we've got the magnetic field sensors just next to it. And they don't want to detect the magnetic field of the spacecraft. So these are the design challenges. So you've all talked today about your design challenges. Solar Orbiter had lots. The most obvious one, I think you probably realize, is surviving the extreme temperature, 600 degrees at the front and minus 180 at the back. As I mentioned earlier, the strategy there is to design a heat shield that can tolerate those temperatures, and a coating, which we put on the outside of the heat shield, and also the high gain antenna. That was a coating that was specially made for this mission. Called Solar Black. It's actually made up out of ground animal bones, which is then burnt. And it makes a very, very black material that doesn't degrade under ultraviolet light. So it stays black. And it's one of the blackest known materials ever flown in space. And we're the first mission to ever fly it. As you're all probably aware, you want to have something that's very black and stays black in order to emit the most amount of heat back into space at the coolest possible temperature. If we would not have black, if it would be white or gray, then we'd be up at 700, 800 degrees. And the material of the heat shield is made out of titanium foils. It's quite a clever design. We've got something like 60, 70 different foils, all in different layers and packs, with a 15-centimeter gap between them, to allow heat to escape between the front and the back layer of the heat shield. So lots and lots of challenges for temperature. I'll say a little bit more as well on the next couple of slides. Then each instrument, as I said, is bringing its own new requirements. This is, if you would just go into a lab and just take every piece of equipment out of there and put it on a spacecraft, each one would want different things. So the cameras, for instance, they want to be cold. They want to have their CCDs down to -60 if possible, to minimize the electron noise. But you've got an aperture which is facing the sun, which is pumping 13 times the amount of solar power that we get here on Earth down the aperture. And so one of the design drivers is to get rid of that heat as fast as possible. So we keep the doors shut all the time until we want to take pictures. Once we've opened the doors, the heat rapidly heats up the instruments and the cameras. And so we've got to dump that out of the side. We have a special radiated design with exotic material straps. I'll say a little bit more about that in a second. Most of the instruments also want to be extremely clean. So some are extremely sensitive to water, so they must be dry at all times. Some are very sensitive to dust. So the coronagraph, for instance, can tolerate no more than a single 100 micron particle in its aperture. So one particle of dust is enough to damage the science. So we cannot allow any dust on the spacecraft that could penetrate the instrument apertures. And we're not allowed to have volatile contaminants either. So as you're probably aware, lots of materials give off volatiles, like paint, for instance, and we have to absolutely minimize that contamination. And for all time, so for the 3.5 years that it took to assemble and test the spacecraft, we had to make sure all of the instruments were kept completely pristine. And we did that by feeding them all with pure dry nitrogen gas for 3.5 years, right up until the point of launch. Some of the instruments, particularly the heliospheric imager, also must have no scattered light. Heliospheric imager is looking sideways from the spacecraft at the solar wind. So the sun is about 1,000 million times brighter than the solar wind dust. And if you would just even get a tiny fraction of the solar light scattered as a reflection back into the heliospheric imager, it wouldn't see anything else but the sun. So we have astonishingly high stray light requirements on this spacecraft. And we're rotating the solar rays back and forward to keep them cool. That's our strategy as we get close to the sun, is to rotate them back. We have plenty of power, but they get too hot if they're normal to the sunline. But by rotating the arrays all the time, you get different scattered light depending on where your solar arrays are. So you have to study all possible cases to make sure that you don't get reflections. Also, some instruments like the magnetometer, they don't want any magnetic field of the spacecraft. They would like the spacecraft to have none whatsoever. And our requirement is really very tiny for a spacecraft of this size. So it's 10 nanotesla. And we had to design the spacecraft with non-metallic materials where we could, or where we couldn't, because there's reaction wheels and thrusters must have magnets. We have to take precautions to offset the magnetic fields by pairing or shielding. And we have some exotic shielding materials to minimize the reaction wheels, for instance. Some sensors, as I mentioned, the electron sensor at the tip of the boom would like to have no charging on a spacecraft. So spacecraft charge all the time in space. There's always charged particles colliding with a spacecraft that charge it up. So if you would have non-conductive materials on the outside, they would develop a static charge. That would then deflect the electrons. And for the low-speed electrons, down to 1 electron volt, the sensor wouldn't measure anything. It would just get bounced away. So we have to make sure the outside of the spacecraft is always less than a few volts, which means everything on the outside has to be conductive. And that's not easy, because you also want it to have other properties, like its thermal properties, or paints, for instance. How do you make paints electrically conductive? So we had to coat them with a special coating called indium tin oxide just to make the paint conductive. So lots and lots of challenges like this. And as well, the radio sensor doesn't want to measure radio waves from the spacecraft, and all spacecraft electrical equipment emit radio waves. it wants those radio waves to be suppressed by many factors, 50, 100 dB in some cases. So a lot of filters, shields, the entire spacecraft is sealed, and we've done the absolute best we can to make sure the fields from the spacecraft are totally minimized. And each one of those, then they kind of contradict some of the others, and it's very difficult to find that sweet spot. If you think about this as a kind of 6 or 7 dimensional space, you're trying to find a point in the middle of this space which satisfies all the constraints at all times. And we found it, but it took us a long time. Then we have, as I mentioned earlier, the strategy is to hide behind a heat shield, and you must hide behind it all the time when you're close to the sun. If you would stray even 3 degrees off the line of the sun would start to heat the side of the spacecraft, and they can't tolerate the heat. And the spacecraft fails very, very quickly within minutes. So it means that your software must be very fast, very responsive. Be able to respond within seconds. If you would have a wheel failure, for instance, you must be able to switch that wheel off and then recover the spacecraft within tens of seconds. At all times, for all 10 years of the mission. Also, we on the far side of the Earth, potentially for up to 80 days behind the sun. And as you're probably aware, the sun is a radio transmitter and it blocks radio signals. So you're actually in a blackout behind the Earth, and that could be potentially for up to 80 days. So the spacecraft has to survive by itself. It means that the software that we load not only has to be fast, but it also be extremely complex. It has to be able to think of anything that could go wrong and take remedial action, put the spacecraft in a safe state, ideally still in an operational state, no matter what happens, for nearly 3 months, which is also quite challenging. And as I said, all of those, all at the same time. So I'm just going to very quickly cover a couple of those. On the left, you see the as-built spacecraft. That was a photo taken just before we sent it to Florida. You can see on the top the heat shield coated in this solar black material. You can see the doors as well, where the instruments, the instrument apertures are behind the doors. On the right-hand side, you see the high-gain antenna, also coated with the solar black material, trying to keep it cool. Then you've got the solar arrays on the bottom. Just behind that solar array, you'll see some white squares. Those are the radiators, and they're coated with a special white paint, actually called solar white, which is a white paint painted on solar black, and then with the indium tin oxide on top of that. And the purpose is really to, take all of the heat from the instruments and dump it out of the side of the spacecraft as fast as possible. So those radiators are very, very high performance radiators. But the most high performant part of that design is what you can see on the top right-hand box there. That's the heat strap. One end is connected to the camera CCD. The other is connected directly to the radiator. And that strap is made out of a material called pyrolytic graphite. And it's 5 times more conductive than copper. It's extremely flexible because this has to survive the launch loads. You can imagine the radiators at one end are shaking up and down like mad during launch. On the other is a very, very sensitive camera. So you must transmit no mechanical loads down this strap, and yet transmit all of the heat loads as fast as possible. So it's a sweet spot in terms of material selection to achieve very flexible design, but with very high conductivity, so 1 watt per Kelvin. So the material we selected there is pyrolytic graphite, never flown in space before. It's been around a long time. It's been invented by NASA in the 1960s, but this is the first space application. It does have the unfortunate property, because you never get a perfect material, that it's brittle. So you have to be very, very careful not to scratch it. Also, if it would break, and there's 70 layers inside, so you can afford to break 1 or 2. If it would break, it generates contamination, and therefore you have to seal it inside a contamination-proof bag. You can see how the design drivers multiply one on top of the other. And in the bottom diagram, you can see there all of the 11 radiators on the side of the spacecraft, each one connected to a specific instrument heat control point. So yeah, thermal design was great fun. Just very quickly, because I'm sorry, but we are under time pressure. This is the testing environment that we did with Solar Orbiter between December 2018 and June 2019. So very fast, actually, 7 months environmental test, about as fast as you can do it with a complex spacecraft. On the top left, you can see the thermal chamber. That's the 6.5 meter chamber at IABG in Munich. And we did a thermal test there just before Christmas in 2018. Then you'll see on the right-hand side of that, the shaker table where we do the sine vibration, and we shake it up and down and side to side. See if there are any resonant frequencies that make it fall to bits. Hopefully not. And as it happened, there weren't any. Top right-hand diagram is the acoustic chamber, where we play loud rock music for 3 or 4 minutes to simulate the launch vehicle. Okay, it sounds like loud rock music. It's extremely loud, so you're not allowed anywhere near the facility when it's on. It will kill you. Then on the bottom left is the mass properties table. So we measure the center of gravity and its moments of inertia as well, just tilt it and rotate it to measure those precisely so we can tune the AOCS, the attitude control, precisely. Box 5, you can see there in the middle in the chamber, which is damping radio waves. That's where we measure all the electromagnetic properties of the spacecraft, check to see how the radio instrument performs against those radio transmissions. So that was a very important and successful test. And then the bottom right is more or less unique for this spacecraft. It's a magnetic test facility. And it's quite difficult to test magnetic field because we're testing the field of the spacecraft is more than 10,000 times less than the magnetic field of the Earth. So you've got to get rid of the magnetic field of the Earth. You can only do that with a special facility. Here, there's one near IBG premises in Munich. So they have massive Helmholtz coils at, I think, 10 meters, or huge coils where they null precisely the Earth's magnetic field. Then you can see for the very first time what is the level of the spacecraft magnetic field. And you really don't know if you've designed it until this point correctly. You could have 50 nanotesla, 100 nanotesla. The goal is 10. And I'm pleased to say we measured 6. So we're very, very pleased with the magnetic design and performance of the spacecraft. So we got into orbit, and then a few months later, we got as close to the sun as we're currently going. As I mentioned, next March, we'll get a lot closer. This was taken at 0.56 AU, so about half the distance to the sun. That's a picture from the ultraviolet imager before it's even been fully calibrated, so it's already stunning. The closest pictures of the sun ever taken. And as I mentioned, next year we're going to go twice as close again. And this is a picture taken by the high resolution camera on the ultraviolet imager. You can see the scale is fantastic. You see similar images from the Earth, to be honest. It's the resolution is good, as good as you can see from Earth. But to be able to take those in space with no atmosphere in the way, it's a huge benefit. And you might have heard the discovery of the so-called campfires. We're trying to understand the origin of the solar wind. Somehow it's to do with how the magnetic field is twisting and connecting in the corona. And these twisting and reconnecting magnetic field lines, they generate intense flares. We can see that this is happening at all scales. And we can see there with the arrow, a tiny emission, what we call a campfire. And if the sun is covered in those tiny emissions, which you can't see from Earth, then that could be one of the explanations for the origin of the solar wind. So very, very exciting already. So even though the mission has not strictly started, it doesn't start until we get past Earth in November, we're already discovering new things. So Whirlwind Tour, sorry it was so fast. As I mentioned, the next event is the Earth Flyby, 27th of November. Get your telescopes out. You might need a big one because it's not so close to the Earth, a few thousand kilometers, I think, but it's possible to see it, I think, with a 10-inch reflector. And that's it. Thank you very much. It was a privilege to talk to you. Now, I'm happy to take your questions.
Well, thank you very much for giving us that talk. It was very interesting. I know I really liked it. We've had some questions coming in the whole time. So I guess I'll kick off with the first question. So from an anonymous audience member, how badly would a coronal mass ejection affect us now, and how much damage could be avoided with some prior warning from solar satellites?
Yeah, it's a very good question. It's very topical. So we don't really know how severe a coronal mass ejection could be. We don't know if there's an upper limit. We know there was one, I think, in 1859 called the Carrington event. We didn't have much technology in those days. We only had telegraph. But we do know it shut down all of the telegraph systems by generating huge currents in the wires. If it would happen now, at the magnitude that we saw then, it would do significant damage. It's possible to mitigate against it. So, for instance, we would have huge disturbances of the power networks, the electricity grids across the world. It's possible to isolate them, protect them, but you need advance warning. We would have difficulties with spacecraft in space. It's likely to significantly affect their attitude control, and maybe even knock them out completely. And it is possible to put the spacecraft in safe mode, but again, you need some warning. Also, it would affect mobile towers for your mobile phones. It would affect the navigation systems, and nearly everything is using the GPS or Galileo navigation systems these days. So it would have a system-wide impact. More or less every system would be affected. And if it would be knocked out for a day, 2 days, could have a serious consequence for society. So back to your question about advance warning. At the moment, we can get a few hours of warning, which isn't really enough. So we're looking at a spacecraft now to follow on from solar orbiter called Lagrange, which ideally would give us something like 4, 5, 6 days of warning. And that's sufficient. So this is what the scientists and the Met Office in the UK, for instance, are aiming for, is to get 7 days warning rather than a few hours.
Oh, thank you. Thank you for that answer. The next question we've had is, why would NASA create a material in the 1960s if they weren't going to use it afterwards? So I think that's about the thermal strap ring, isn't it?
Yeah, so it's the first time in space, to my knowledge, but it has been used many other places on Earth. I think it's used a lot in the medical industry, for instance. So I haven't done a study of this material outside the space industry, but I do know if you would Google it, pyrolytic graphite, you'll see that it's used in many, many places. Underwater submarines, nuclear reactors, that kind of thing. So it's ubiquitous on Earth, but it's never been flown in space. I think partly because it's just too difficult to handle, but we knew that we needed the properties of that material, so we were just careful to handle it correctly.
Okay, that's interesting. Another question that we've just had is, what was the most critical part of the project? So I guess that means before it became an actual mission, maybe.
Yeah, sorry, I'm not really sure about when you say before it became a mission.
Yeah, no, sorry. As a before it was launched, I guess. If it was the project,
I get your point. Yeah, so I mean, I hinted at the magnetic field. We call that kind of hidden contamination. A lot of things you can measure, but you can't measure a magnetic field of 6 nanotesla on Earth. So all you can do is hope that you've designed it correctly. You can measure the magnetic fields of individual components like your thrusters and electrical boxes and so on, and prove to yourself that your equipment level, hopefully you've got low magnetic field. But at spacecraft level, all you can do is assemble it and hope that your model is finally proved valid. It's also astonishingly easy to accidentally magnetize a spacecraft. So if you would bring, say, a steel screwdriver to the spacecraft and twist a screw, you would magnetize that screw. And if you would do that with a few thousand screws, then you've blown your magnetic budget on your spacecraft. So we had to take very strict precautions on no magnetic materials within 3 meters of the spacecraft ever, on pain of death. So because it's simply impossible to know if you've contaminated the spacecraft until you're right at the end of the test sequence. You've built it, you've tested it, you put it in the magnetic facility, then you measure it. If you've screwed it up, that's it. Ship it back to the integration site, take it to bits and start again. So we were really nervous. We trusted our models, but you never know until you measure. I think you've probably said that earlier in your prototype demonstration. You never know what you're designing until you actually measure it. So that was a really critical point. Another critical point was the heat shield. It's very difficult to test something that can withstand 600 degrees centigrade. It's 2.5 meters across. we had to actually build a special part of the thermal chamber simply to generate enough heat to radiate at the heat shield to get it up to the right temperature. And that heating device itself, never been built before, had to be actively cooled. It took probably a year to build the test facility to test the heat shield. And that's why probably part of the design is like it is. If you would have to have a complete facility to test the spacecraft at 600 degrees, you probably haven't got enough power in the local vicinity to cool the heating plate to test at spacecraft level. So we could only test something at heat shield size, and then everything else has to hide behind the heat shield. So, testability is a key part of the design, So those were two key moments where we had to take, very special precautions. And fortunately, the heat shield was fully qualified. Heat shield is very interesting design. It's quite fragile. It's built on a carbon fiber substructure. Carbon fiber itself is quite challenging to manufacture. And in fact, when we manufactured that carbon fiber substructure, we were only able to make 2 or 3 copies before the process failed. So you cannot guarantee always to be able to make perfect carbon substructures for titanium heat shields. So we had made just enough for the mission. Had we broken any, we would have really struggled to have had enough material to make another one.
That's very interesting. I didn't really think about that side of it, but that's slightly worrying. Another question which kind of follows on from that one quite quickly is, what was the biggest failure, if any, during the testing campaign?
You're asking me to declare my secrets now. Yeah, it's easy to make mistakes. What you plan for, you tend not to make a mistake. It's what you don't plan for, which is the crazy, silly things. I'll tell you a little story then. Obviously, we have to have everything perfectly clean. I talked about volatile contaminants. There can be no volatiles on the spacecraft. They have very damaging effects on things like the spectrometer camera. Now, when we were assembling the solar array wing at the solar array integration site and testing it, one of the contractors decided to put bitumen on the roof of the facility. And unfortunately, the volatile components from the bitumen entered the clean room and deposited themselves naturally and nicely on the surface of the solar arrays. So when we came to measure the contaminants of the solar array before we shipped it to be installed on the spacecraft, we find it was covered in bitumen. Quite frightening. Nevertheless, it was possible to clean it, so after about a week of very, very careful cleaning, be careful what solvents you used on something that's already designed for a very exotic environment. But we were able to finally clean it. It took us a week. But these are the kind of mishaps that you get that you can't predict, or maybe that was predictable, but you will always end up with something like that. Some crazy thing will happen to your mission that you have to try and recover from. But yes, we managed to clean the solar arrays and back to pristine condition and then install them on the spacecraft. But plenty of, I would say, polarity errors. It's very easy to get something upside down. That sounds a bit stupid, but certainly in terms of phase of electrical signal, you can easily get it 180 degrees out of phase. Lots of tests you do at electrical level on your harness, for instance, you're testing just for continuity and isolation, so checking that there's a current and checking that you're not got any current between your wire and any other wire. But you're not normally checking for phase of alternating current. And we had a few cases where we'd accidentally got the out and return wire mixed up in the database. When we connected it to the equipment, it was exactly 180 degrees out of phase. So you get plenty of polarity errors like that. In fact, one of the new tests that ESA asks for these days is to make sure that you do a test at spacecraft level that proves that the sensors are wired correctly in phase with your actuators, and you haven't made some stupid polarity error somehow down the chain. You test everything at equipment level, but at system level, it's very difficult to do an end-to-end check that your sensors are correctly wired in terms of polarity with your actuators. And so ESA is now asking for very sensibly a test that proves that when you say go left, you go left, but not right. So we managed to find a very neat way to do that with Solar Orbiter. I won't go into that. It take me another half an hour. You've probably come across polarity errors already with your designs.
Right. Okay, I think we have one final question, and then I think that's all we have time for. But it's been so great to talk to you, and thank you for compressing the presentation for us. But the final question we have is, how can Solar Orbiter's onboard computer support such complex software? What does it have that other regular spacecraft don't have?
I don't think it has anything special. I mean, the onboard computer is just a normal onboard computer. We took one that existed from a previous mission. So we don't redesign something if it doesn't need to be redesigned. I don't know any details about the computer, I'm afraid, in terms of its capacity, but it was full. We loaded it. You know, you have to normally make sure you've got some spare capacity so that you don't overload your real-time computer and it runs out of space and starts to drag out of real time. And so normally you would aim for maybe a factor of 2 between your designed capacity and your actual capacity. So nothing special about the computer. Really, though, the software itself just requires a lot of design effort and testing. So we had a lot of simulation machines, 24 simulation machines running night and day, testing something like 105 test cases continuously. So every time we change a line of code, we'd rerun the whole, I can't remember how many lines of code, let's say 100,000 lines of code, all the way through all possible test cases. So, huge effort to test the software. Maybe it's not fantastically complex for a ground-based use, tens of thousands of lines of code is nothing really, but in space, you have to be sure that there is no error in any of the line of code. Or, as I said, we're 80 days behind the sun, potentially. Any single code error could lead to the end of the mission. So we have to test it to death. That's really the unique feature.
Okay. Well, I think that's all the questions we have time for, unfortunately. But if we get any more, then we'll try and pass them on to you. But thank you so much for coming and speaking to us and being part of our competition day. We know we've had so many great questions coming in, and I've really enjoyed listening to it. So thank you so much.
Thank you. I appreciated the questions. They were great. Thank you very much. And it's a privilege to be here tonight.
Oh, thank you. Okay, so we'll go on a short break from the stream just now, probably about 2 or 3 minutes. Then we'll come back with what everyone is waiting for, which is the award ceremonies to saying who's won and everything. But I know you've all enjoyed Solar Orbiter so much. But yeah, thank you again.
Cheers.
Okay, hello everyone, and welcome back to the satellite design competition. I hope you enjoyed the talk from Solar Orbiter there. That was really interesting, and sorry we overran a bit, but we had such good questions coming in. But now it's time for the award ceremony, and I'd just like to take a minute and delay the results a little bit longer to say thank you to a few people. So first of all, I'd like to thank all of the UK SEDS volunteers. So Sharon, Sam, Gotham, Lee, Holly, and Yulia, who have helped create this the whole year and make this competition possible, and just really put in loads of work behind the scenes to make everything happen. I'd also like to thank our mentors for this year. So Dawn, Elaine, Mark, James, Pat, and Mike. You've been great mentors and really engaging with the teams. And as you've seen from some of the presentations, kind of going above and beyond and really helping the teams with things. I'd also like to thank our organizers. So from SSPI, Robert and Tamara, they've been great at giving us advice and support and providing us with our mentors. And then from Airbus, I'd really like to thank Phil and Ollie, who have been really, really great at supporting us and helping us organize these great talks we've had today. I'd also like to thank Phil and Alex again as the competition judges, so for helping us judge all of the presentations that we had today and provide some really useful kind of insight and questions for you all. And then just again to thank SSPI as our co-organizers and Airbus for sponsoring the satellite design competition. And then also to thank all of the teams for taking part as well. But I'll come on to you again in a minute. So our competition prize categories that we have is the overall winner. So we have the overall winner of the competition, the best CDR report, the best extended design report, the best test readiness review, the best presentation, and the best prototype. And so the marking has been done by the mentors, and then also moderation marking has also been done by a single mentor who has really helped us out. And then obviously there's some categories that are going to be different to others. So due to the pandemic, in the end, only Cranfield could build. So only Cranfield have entered the TRR and prototype categories. So they have won those categories. I'm sorry for ruining that surprise. But yeah, it's been really good to see a build happen. And it's just been great to see all of the work and effort that all of the teams have put in this year. So thank you very much. We'd like to thank you all of our finalists, for putting in so much work, creating such amazing mission patches, and for committing so much time to this. I hope you've all really enjoyed the competition and got something out of it. Hearing some of your presentations today, I think you have, and I know it's been great for us as well. So there we'll start off with the best CDR report. So this was based off of the marking. So the best CDR report is going to Cransed's vicinity. So yeah, that was the best CDR. So congratulations. It feels very weird doing this by myself to a computer screen, but congratulations, Cranfield. It was a great report. There were some other really close reports that were amazing. I wish I could give marks to everyone, but in the end, this is what was chosen by our markers. So next up, we have the best extended design report. So this is the second large report, and this is Strath AI, so Strath Squared. You've won the best EDR report, so your extended design report. Again, very, very close call, this one. There was I think 3 teams who were right at the top of the EDR report, and so it was really, really close. But in the end, you've done it, and you should be very proud of yourselves. You put in so much work and effort, and it really shows. The best TRR, so as I previously mentioned, Cranfield were the only team in the end who could enter the TRR due to the coronavirus restrictions, but that doesn't detract anything from their achievements. They've done an amazing job at building and testing, and as we saw in their earlier presentations, there's so much work that you've put into it, so much time and effort, and it's really, really been great to see. And you've gotten so much out of it as well, so that's great. The next report that we'll be going to is the best presentation. So this was based off of all of the presentations that we saw today and judged by Alex and Phil. And again, this was a super close one. I know they had a really hard time kind of distinguishing between them all, and they were debating for quite a while. But in the end, it's gone to Cransets for the best report, the best presentation, sorry. Yeah, so you should be really, really proud of it. There were so many teams that had put in so much good work today. but it's very difficult to pick a winner. But yeah, you've done a great job, and it was a very clear presentation that got across your goals. Your preparedness for your questions was also excellent. So I know that was good. You should be very proud. And then the best prototype is the next category. So that again, due to the coronavirus restrictions, is going to go to the vicinity. It just really was an outstanding prototype. I'm sure you would have done very well if everyone could build as well. It really was great to see it in action and great to see the mystery room come to life. So that was incredible. So thank you very much and well done. And then the final category is the overall winner. So we're going to do a third, second, and first place for this one. So because it was very close. So this is an accumulation of the marks across the CDR, the EDR or TRR report, and the presentation today. So it's an accumulation of those marks that goes into deciding the overall winner of the competition. So in third place, we have Leicester. They've got third place overall based off of those 3 reports. So you should be very, very proud of yourself. It's great work that you've done, and it's been amazing to see. Second place is Strat Squared. So congratulations, put in so much amazing work, and very, very well done. And then first place goes to Cransed's Vicinity. So thank you very, very much to all of the teams that have participated in the competition. You all put so much work in. If you haven't won a specific category, it doesn't matter. You've put in so much time and effort and learned so much, and we're really blown away with the quality of the reports this year from everyone. So you should be very proud of all the work you've done. It's just been amazing to work with you all this year. You've really made it a pleasure to run this competition and to kind of do this. It's been very, very fun and enjoyable for me and the UK Sets team. So thank you very much. And I hope you've all got a lot out of it. But yeah, go and celebrate now. And thank you so much for participating. We'll be in touch with all of you in the coming week or so about certificates and things. And there's a form to fill out to give us some feedback about the competition. Yeah, so let us know what you think in that, and let us know your details for all team members. Even if you haven't won a specific category, then you can still get a certificate to say you've partaken in the competition. So thank you very much. And thank you all for sticking through it throughout the whole day and all of our technical issues that we've had. I hope you've all enjoyed it and enjoyed our guest talks. Yeah, thank you very much, everyone. And I hope you have a good evening, only 20 minutes behind schedule. Yeah.